Upasna, you may start. Please introduce our next speaker, Miss
Yes,
Upasna.
yes. I would like to welcome everyone once again on behalf of Center for Climate Change and Water Research, Suresh Kanviha University, Jaipur, Rajasthan, on the 10th day of Summer Winter School in Geospatial Science and Technology, Level 1 program sponsored by DST. Now, let me introduce to our first speaker of day 10, Dr. Deepak Kumar, sir. Dr. Deepak Kumar sir is an academic research professional with intensive experience of over 10 years in academic research and over 7 years in PG teaching in the field of geospatial technology and application, urban planning, remote sensing, analytical research methods. He is presently working as an assistant professor in Amity University, Uttar Pradesh, Noida. He also holds two government-sponsored research projects as sole principal investigator, namely hybrid urban landscape analysis for green smart cities through geospatial technology, sponsored by the Science and Engineering Research Board, Department of Science and Technology, Government of India, and meta sensing of the urban footprint for airborne synthetic aperture radar data sponsored by Space Application Center, ISRO Ahmedabad. He has been revisiting a wide range of issues associated with traditional research activities, but has his own injects of thinking on non-traditional, challenging areas topic for the exchange of research activities. More previously, his teaching and research interest lies around spatial information sciences, spatial data modeling and analysis, spatiotemporal data management and geovisualization, spatial and fractal computing, spatial predictive analysis, spatial cognition, geoprivacy. As principal investigator of two government-funded R&D projects, he has been involved in project development and management, laboratory management, supervision, and teaching of undergraduate, postgraduate, PhD students and researcher, training of other researcher, publication and grant writing. Dr. Kumar sir has directed cross-functional and research teams using interactive and motivational leadership, acknowledged for coaching, guiding, and mentoring team members to achieve resource wise productivity and optimization. He has also leveraged skill in analyzing collected information, comparing several types of research data, and engaging in safe research activities. Specializes in urban research, having worked on the development of techniques and methods for monitoring of urban landscape. He encourages researcher to develop skills, knowledge, and expertise in aspects of research management as a budget and project management, teaching, publication, and other conference appearances, outreach activities, and membership of committees. His vision is to create a passion for high quality innovative research and teaching while inculcating scientific temperament, knowledge, and human values with the aim of creating clean and capable manpower in the country. With that, I'd like to invite Dr. Deepak Kumar sir. So we are very delighted to have you here and request you to start with your sessions.
Okay. First of all, thank you, Pasna, for such a long introduction to me. And first of all, I also would like to thank Dr. Shruti and Dr. Suraj Varun to invite me on this platform to interact with all the participants of this winter school. So today we will see some of the issues related to geometrical errors and how we can perform geometrical corrections to the images, whatever we are requiring from different satellite platform. So I'm just sharing my slide. Just let me know once it is visible. Is it visible?
Yes, sir. Yes, sir.
Yes.
Okay.
So,
So
please
today's
keep it
topic.
in slideshow mode, sir. Please keep it in slideshow mode.
Okay. Okay. Just a minute.
Yeah, now okay, sir. It's okay, sir.
Just it is fine now.
Yeah, yeah, yes, sir. Sure, sir. Yes.
Okay. So today's topic for the day is geometrical correction. So we will see that how these geometrical corrections are responsible for image corrections to the satellite acquired data set. So coming to the uh, outline of my lecture. So first of all, I will say something on remote sensing basics, because it is important to say, means it is important to learn that what are the remote sensing aspect that is required for these corrections, and how we are going to acquire remote sensing data set, because depending on different satellite platform, different sensors, we are getting different kind of geometrical errors. What are the remote sensing standard for data acquisition, how we are going to implement it, and at the end we will see some of the case study and application, that how this geometrical correction method will help you out to improvise your data set. So these are some of the things. So I think that my earlier speaker might have covered the concepts of remote sensing, but just to give a glimpse of that, you know that it is a technique of obtaining information about object without making physical contact with it, and there are several steps that are involved with remote sensing process. So these are some of the steps that are involved with the process, and you can see here is that in between satellite to the object there are certain medium, and each medium is contributing different kinds of error in the data set. So today we will see that how geometrical orientation of the satellite, how geometry of the object, how geometry of the means sun angle, how geometry of the earth curvature is going to affect your acquired data set from different platform. So these are some of the systems that are involved with remote sensing process. So first is energy source. So it is one of the contributing factor also in giving some kind of errors to your data set. Similarly, platform means on which your satellite sensors are typically embedded, and those are helpful for carrying out your sensors. And obviously your sensor is also one kind of system that is enabling you to capture the data set. And after that you are getting this kind of data recording and transmission capability from this satellite platform. And once your data is received at the station, your data may have a different kind of error, like radiometric error, geometric error. So we do pre-process the data set to make it more user friendly. So these are some of the aspects of your remote sensing. And as a part of that, we know that if you are capturing the data set, we are having different modes of data capture. Either we can capture the data set in visible spectrum, or we can capture the data in thermal spectrum, we can capture the data in microwave spectrum. But one interesting thing that is uh, that is more required to learn here is that uh, means each one of this spectrum is responsible for giving different kind of error. If you are working in thermal domain, so the emissivity of the object will be giving certain kind of error to your data set. If you are working in a microwave system, then your orientation as well as the properties of the object will give different kind of error to your data set. If you are working in a visible spectrum, so your light intensity, your reflection, your medium of transmission, all will give different kind of errors to your data set. So in part of that, uh, geometrical errors will play a very vital role in the data set. So one of the live example you can see here is that while capturing remote sensing data set, we are having this kind of options with us, that if you are interested to know about an object in precise detail, so we can use this crane mounted sensor. You can see that one crane is there that is holding a sensor, and that is looking around a particular object or feature. So here we are getting a more precise details of an object. But the thing which is more associated here is that the data what we are getting here may be inaccurate, because if this platform where this crane is mounted is moving, so there will be vibrations in this platform, and that will give error to your data set what you are capturing from the sensor. So this kind of things is there. Similarly, if you go to this airborne platform. So here also, if there is a turbulence in the air, so due to turbulence in the air, the data captured by the sensor which is mounted on this platform will also give this kind of error. If you are using a balloon platform, here also the same kind of issue will be there. So if there is a drag and drift force in the wind, so that will also give a problem to your data set. So this kind of things will be there. So that's why whenever we are going for remote sensing planning, so we have to do this kind of thing. We have to make a concrete mission plan. After that, you have to select particular kind of sensor, that which sensors are responsible for which kind of data set. So depending on our application, we are going to use different kind of sensor. And after that, once you have selected your sensor, when you have done with your mission plan of the remote sensing process, you have to use appropriate kind of reception system, recording system, and processing of the data set. Because if you are getting microwave data set at your ground station, the processing step will be different. If you are getting optical data at your ground station, your processing step will be different. Similarly, in case of analysis also, the method what we are using for optical data set will be different from the method what we are using for microwave data set. So depending on the data type, depending on the platform type, the system in remote sensing will be changing. So as I said, that depending on the uh, requirement of details, we are using different kind of platforms. So that may range from ground based platform to the satellite based platform. And uh, whatever platform we are using, so each platform is having its own complexity in terms of geometrical error, in terms of your radiometric error. So if we are using this ground based observations or ground based station, so here, due to movement of your platform, there will be vibrations in the system. Due to that, your sensor will be getting affected, and that will give geometric error. Similarly, in low altitude flying system, due to that drag force of the wind also, that will also give a problem to your data set. Similarly, in high altitude image acquisition also, due to this clouds, due to this turbulence, again you will be getting this kind of error. Similarly, in satellite data set, also satellite based platform also, due to off track of your satellite system, you will get some kind of errors. So these are some of the things that you have to take care, that how to monitor the data set. And if you are getting some kind of error in your data set, so what is the method of those improvisations, so those part we will see. So you can see here is that in remote sensing, we are having different kind of system for data acquisition. Either we can acquire the data in pan mode, that is a simple black and white images, and that is covering a typically visible spectrum. Similarly, we can acquire the same visible spectrum in multiple channels. So there we are getting multispectral satellite to acquire this data set. And even we can acquire the data in radar domain. And nowadays we are using hyperspectral system also to acquire the data set in very narrow channels. So these are some of the satellite based data acquisition system that is giving you capability to acquire the data set about different objects. But each of this data type is having its own error system. So uh, the main thing that you need to understood here is that if your satellite is revolving across any orbit, so typically this kind of orbit will be there, which is going to cover your whole globe. So you can see that this is a typical Landsat or orbital track in relation to its equatorial crossing every 103 minute. So you can see that means one pass is covering almost one part of the globe. So whenever it is covering, there is no linear track here. You can see that there is a curvature kind of thing due to Earth curvature. Also, there is very narrow space at the poles, and there is uniform space at the equatorial side. So due to this, also we are getting some kind of geometrical error in the system. So we will see with the help of an image that what is happening practically if this kind of system is working uh, around your satellite system. Similarly, if we combine all these uh, passes of satellite system, you can see that how much intersections are there, how many intersections are there, and due to these intersections also we are getting some kind of geometrical error in the data sets. So you can see that this is one example of a spot high resolution data system. Suppose if your satellite is programmed to follow the track like this on another track, but due to your satellite uh, data requirement, you are shifting from off means nadir mode to off nadir mode. So in that case also your data will be getting affected and your data need to be corrected. So these are certain a live example where we are requiring to do these geometrical corrections. Similarly, you can see that uh, even your data is being captured at d today date, and if you are capturing the same data at d minus 5, and even if you are capturing the same data of the same area at d plus 5 day or d plus 10 day, so there will be difference in the data set in terms of geometry, in terms of accuracy also, so that need to be corrected, and those are being done with the help of geometrical correction. So these are some of the live cases where we are trying to improvise our data sets. So these are some of the typical radar images you can see in this slide. That's that if you see this image, you will be unable to perceive any one of the feature, and you can think of the error, that what kind of geometrical error it may give, even if a small feature is getting higher brightness value or higher back scatter value. So it will be difficult for us to quantify those values. So for that, we should know that what kind of geometrical problem is happening in this kind of images, so we can pinpoint the error, that how much error is happening in that images. So this is one example of your radar image, that how radar image is giving uh, 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 perseverance to your images kind of thing. Similarly, you can see that even we are unable to identify the feature, so you can think of that how you will quantify the feature length, feature area, or feature perimeter, because it will be difficult for you to understand that what kind of image it is. So if you are unable to understand that what kind of image it is, then how you will quantify these features? So because in geometry, if you wish to quantify, either your feature will be a point feature, line feature, or polygon feature. So even we are unable to pinpoint that whether it is a point feature or line feature. So how you will quantify this thing? So for this also, your geometrical correction is too much required. Otherwise, a lot of error and bias will be there in the final calculation. So even in this optical image, you can see over here is that you are getting this kind of shadows in the background. So due to these shadows also, you will be getting a lot of error in your data set. So we need to quantify those errors, that what kind of error we are getting due to this shadow geometry. So the feature geometry will be totally different from the shadow geometry. So the shadow will also give a very a different kind of error to the object geometry. So these are interrelated thing, and we need to quantify both of the things. So in order to do that, we are going to study about this geometrical errors. So these are also one of the things you can see over here is that due to orientation of the satellite image, you can see that little bit oblique image you are able to see here is that, and due to this shadow that is raised due to this building also, there is a force shortening of these images also. So due to that also, we are unable to quantify the exact length, breadth, and dimensions of this object, and that is one of the also major issue that need to be solved while processing this kind of satellite images, because many of the time we are interested to know that what is the length of this bridge, what is the length of this road, what is the dimension of this building, how much area it is capturing. Suppose in case if some revenue officials is there, so they should know that what is the dimension of this building, so they can properly do the taxation of this land parcel. So like that, we need to quantify many of the time. But if there is a geometrical problem in your images, so it will be difficult for us to quantify the uh, dimension and length of your land parcel with precise details. So for that, we need to improvise our images. So this is also one of the live example where we can see that how your geometry of this building is going to give a error to your data set, even though it is a very high resolution images. But still, due to orientation of your image, we will be giving some kind of error to your final quantification. You can see that little bit tilt is there in the image. So due to that tilt, you are getting this shadow. So actually your image is supposed to give the exact dimension of this feature, but once you will quantify it, due to this skewness in this feature, we will be unable to get this exact dimension of this feature. So this need to be removed uh, from these images while doing the final processing. Otherwise the data what you are getting at the end may have some error with certain factors. So we cannot process those images, because if you quantify suppose this building dimension as 100 square meter, and if you go to ground and you are identifying this as a 110, so there is error of 10 meters. So you cannot rely on the satellite data set in that case. So that's why in order to properly match your satellite data calculations with your ground data calculation, we are doing geometrical corrections in your images. Otherwise many of the time your satellite data will be not reliable to many of the user, because all users are not that much of tech savvy, so that they will be going for field check of your finally processed data set. Okay, so in that case we are trying to identify that what kind of errors is there, and for each kind of errors we are going to apply different kind of corrections system. So you know that in remote sensing we do have different kind of data format, and typically in remote sensing we are having two kind of data format. One is raster format, one is vector format. So in raster, typically all the satellite images what we are getting is in raster format. So those raster format is nothing but those are the collections of dn numbers, and those dn numbers is telling about the reflectance or radiance values in different spectral band. So we need to convert those uh, raster data set to make it a vector data set in order to compute the dimensions of each and every feature. So whether it is a point feature, line feature, or whether it is a polygon feature. So first thing is that we need to process these images, and after processing we need to quantify those things. So those are the things that is associated with these images. So the major thing that is associated with satellite images is that it can cover very large area at very short span of time, and it is also a cost effective thing. And and as you are able to get a temporal images ranging from 1 week to 1 month, so it is also time efficient. So at very less span of time you can do the remote sensing of very large area. So these are some of the advantages associated with satellite images, but even though these advantages are there, so due to certain kind of errors we are getting stuck somewhere, that we cannot rely fully on the satellite images. So that's why we are going to know about this geometrical correction method and how this is affecting your data set, so that you will be knowing. So in order to make your data set more reliable, so we are going to develop certain kind of framework, that is remote sensing standard system. So here we are going to have a certain framework which is guiding you that what kind of a standard should be there for your data set. And you know that we are going for a remote sensing data acquisition, and after doing your data acquisition we do some data processing kind of thing. So these include your pre-processing part, that what kind of pre-processing thing we can apply to your data set. And after performing this pre-processing part, we do perform certain post-processing thing. So we will see each one of these step, that what it involve, and how each and every step is going to give you a better quality of the data set, because everything is associated with the quality of your data set. If your data set is properly fine, then only you can go for this kind of accuracy, accurate data set. Otherwise whatever analysis you are performing, your analysis will be good, but your accuracy of the analysis will be bad. So you cannot use a bad precision analysis for your real time application. So in order to do your real time application in a better manner, we are going to make your data set more standard. So for that we are going to uh, perform this kind of steps in the system. So you can see that each one of these step, even in a even at the stage of data acquisition, whether it is a platform, whether it is a sensor, whether it is a transmission, whether it is a reception, whether it is a operational management, we do have certain kind of system that is getting involved with that. Even we are using different platform, whether it is a spaceborne, airborne, and ground based platform. So in each one of the platform we are having certain issues, so we need to remove these issues in order to make our data standard. Similarly, if we are using different sensors, so the sensor is having different kind of issues associated with this, and due to that also we are getting this error. So we need to standardize our sensor data acquisition system also. And even in data transmission, some of the time if your data that is being transmitted from satellite system to the ground based system is not a standard, in that case also means there will be leakage of the data set, there will be distortion of the data set, and due to that you will be unable to get a proper data set at your receiving end. So even though many of the time your data is bad or corrupt data set, but at the receiving end we are able to decipher the system whatever is coming from your satellite platform. So those things is also taken care by data reception team. So this is some of the part that is involved with your data acquisition system. And after that, coming to your data processing part, so you can see here is that there are certain processing technique ranging from imaging, processing, radiometric correction, systematic geometric correction. So this systematic geometric correction is one of the major thing that is going to control everything. So many of the time we do have satellite parameters with us. So we do apply this satellite parameter to make our data set correct, because many of the time what will happen is that suppose your satellite was programmed to fly at 700 kilometers above the ground level, but your satellite is flying at little bit lower than that, 695 kilometers above the ground level. So in that case there is a difference of 5 kilometer. So how to correct those things? Because due to that drop in 5 kilometer, your data will be little bit disturbed. So how to means modify those data set? So for that we are doing certain kind of systematic geometric correction, because the error we are getting in the data set is due to the system of your data acquisition. It is not due to the sensor. So once you are done with that, after that we are going for precise geometric correction. Means if there is error in terms of your geometry of your data set, so in those cases also we are going to identify those kind of problem. And in addition to that, we are also performing ortho rectification, that we are making sure that there is no shadow effect in your data set. And once we are done with that, we are trying to means individually mosaic different pieces of the data set, because whole the complete area will be not covered with a single set of images. So it may involve multiple images for a larger area. So in that case also we are trying to means mosaic multiple satellite scenes together, so that we will be able to cover the larger area. So those are some of the things that we need to take care, that we need to process the acquired data set, and after that we are generating different data product out of that. Because many of the time we are requested to generate our data product in terms of image format. Sometimes we are requested to generate our data product in vector file. So depending on that we are generating different kind of data format, and those are in order to ensure that the data product what we are going to generate and the processing technique what we are going to perform is correct or not. So we are using certain management system, so that is controlled by the processing system. Management means each and every process what we are applying on the data set is properly running or not. So these are some of the steps that is involved with this kind of data processing. And at the end we are going to check our image quality, that whether our data is geometrically correct or not, whether our data set is geometrically correct or not, whether our data set is spectrally correct or not. And once everything is fine, then we are going for compression quality, that suppose if you are having a 1 GB of data and we need to transfer this 1 GB of data from one system to other system. So many of the time we do have constraint with our LAN connectivity or internet connectivity, so we cannot directly send 1 GB of the data set to other systems. So we do need to compress those data set from 1 GB to 500 MB or maybe 750 MB. So after compression, whether we are able to maintain the data quality or not. So at the end, we are making sure that we are using means appropriate compression technique, so your data quality will be retained. We will be not using means losing the data quality. So those are some of the things that are associated with the image quality. So this geometrical correction is also one of the part of your image quality, that you are making sure that whether your data is properly processed or not, because at the end you have to use this data set, and that data set should be properly corrected in terms of radiometry, in terms of geometry, in terms of your spectral correction. So these are some of the things that you have to take care. So once you are done with that, so these are some of the post uh, uh, processing technique, that in order to means make your data set more visually appealing, visually corrected, we are applying certain filter, we are applying certain image restoration technique. Sometimes we are interested in getting more data in informative data set, so we are also applying multi-source data fusion techniques. So these are some of the things that we are trying to do with this data set. And sometimes we are having different data sets, so we are interested to extract different feature from those data set. Like some of the time you are having thermal data sets, so from thermal you are interested to know the temperature values of different features. So we are post processing with certain a standard technique, and we are trying to extract this temperature value from that satellite data set. So those are also some of the things that we are applying to this data set. And likewise, if we are having certain soil moisture data set, so from that also you can always quantify that amount of soil moisture from that data set. And sometime we are also interested to know that elevation values at a particular point. So if you are having a digital elevation model data set with you, so you can always know that what is the spot height of a particular point, what is a undulation in a particular area. So those kind of things also we can derive from these things. So those comes under the part of your remote sensing information extraction. But for that we are required to have those kind of data sets. Otherwise we cannot perform this kind of information extraction from those data set. So after that means we are also performing this kind of steps, that is calibration, validation, data management services, and at the end we are going to apply this data set for different applications. So those part also we will see that how we are going to apply this uh, data set for different application. Because many of the time you, in order to make sure that your data set is correct or not, so for that we are doing the calibration of our instrument, calibration of our imaging system, calibration of your images. And once you are done with this calibration, we are going for validation of your data set and validation of your algorithm. So all those things has to be managed in a proper manner. So at the end you have to utilize this data set for different application. So whatever application you are going to use, that should be properly managed. So for that we are going to use this kind of methods. So if you see the typical definition of your geometric correction, so it is usually necessary to pre-process the remotely sensed data and remove geometrical distortion, so that individual pixels should have a proper xy location. Because if there is a variation in xy position of a any point, suppose if there is a point on your map and that is shifted with certain error of lambda x and lambda y, so in that case it will be difficult for you to do any planimetric calculation. So you are making sure that each and everything is properly placed. Because in remote sensing you know that there will be only three features: point, line, and area feature. So this point feature has to be properly located, line feature has to be properly aligned, and your polygon feature has to be properly shaped. Otherwise the calculation what you are going to make at the end will be not corrected. So so these geometrically corrected images are used to extract this at last line you can see over here is that geometrically corrected imagery can be used to extract accurate distance, polygon area, and direction bearing information. Because many of the time due to error in your data set, even road network is is aligned in a particular direction, will look like that it is aligned in a different direction. So those scenario I will just show in my upcoming slide, that how things are happening. So typically coming to this error, there are two type of error in your remote sensing system. One is internal error, one is external error. And if you attach to the geometrical property, there will be internal geometrical error and one will be external geometrical error. So it is means prerequisite to know that what kind of error is there in your remote sensing system. So even coming to this internal and external error, you can further classify this kind of error into systematic and non-systematic error, because many of the time you will be knowing that what kind of error may happen in your data set. So those will be coming under the category of predictable or systematic error. There will be certain type where you will be not knowing that what kind of error may happen in your system. So that will be coming under the category of non systematic, and that is also known as random error. So many of the time systematic error is easier to identify, and we can always do certain correction to those systematic error. But in case of your random or non-systematic error, it is difficult for us to perform certain corrections to that, because we are not knowing that what kind of error may happen to your data set. And once it has happened, so there will be a lot of hit and trial to improvise your data set, but at the end we will be unable to know that whether our data is correct or not. So coming to the part of your internal geometric error, so this is happening due to the combination of your earth rotation and curvature characteristics. So we will see this example, that how due to this earth rotation and curvature of the earth is going to affect your data set once you are doing your remote sensing. So this kind of errors are typically known as systematic error, because you know that there is a particular rotation of earth, that it is rotating from west to east. So due to that also, you will be trying to compensate those kind of error in your programming itself, so you will be not getting any error in the data set. So these are identified earlier, means before the launch of your satellite itself, that if you know that there is this kind of error is going to happen in your data set, so you will take care of those kind of error, and you will try to avoid those error in your data set. So these are certain kind of category, like askew caused by the earth rotation effect. So we will see that how this askew is going to affect your data set. And beyond that, you will also see that due to a scanning system also, many of the time you are going to get different kind of resolution cell in the data set in terms of your DN numbers. Because suppose if your satellite is programmed to give a date, means pixel size of 3 by 3 meter, and due to this a scanning system failure or scanning system shift, you are getting a 3.5 meter of data set, or you are getting a rectangular data set. So due to that also, we will see that what kind of error is going to happen. And sometimes you are getting error due to this relief displacement, and sometimes you are getting due to this tangential scale distortion. So those kind of error we will see, that how this internal geometric error is going to affect your data set, that what kind of error is there. And you know that this image offset or askew, that is caused due to earth rotation effect. So many of the sun synchronous satellite are normally in the fixed orbit that collect a path or swath of imagery as the satellite makes its way from north to south pole, that is descending mode of data capture. And due to that also we are getting some kind of error. So I think one picture will be more useful for you. So this picture I think is self-explanatory, that I have collected from Jensen to book, and it is saying that your Earth is rotating from this west to east direction. You can see in this slide, and your satellite is coming from north to south. You can see over here. So your satellite was expected to give a data set like this. Means these are certain scan lines with different DN numbers, but due to rotation of the earth, you can see here is that one patch of the one block of this data is getting shifted right side. Are you able to see this thing, that you are getting this data shifted to right side? So due to that also, you are getting geometrical error. You can see that you were expected to get data like this, but you are getting actual data like this. So typically what we are doing is that we are filling this gap with zero padding or zero data we are putting here. So there will be no additional data that will be coming unnecessarily to our image. So typically we are doing like this, but still this is error in your data, so we need to correct this data set. So at the end, once we are going to apply this actual data to the ground, we are not getting any error. We will be not getting any error to that. So this is one of the error that is happening due to this rotation of the earth. You can see here that due to rotation of the earth we are getting this kind of data. So this is systematic problem, that you know that this will be happening. You cannot anything to this kind of system. So this is also known as a internal this thing. So similarly, due to a scan system also, we are getting certain kind of errors. So we will see that how this scan line system is also going to affect our data set. So you can see that your sensor was programmed to collect the data set at the nadir. You can see that your data was supposed to collected at the nadir point. So if it is shifted this left side, you can see that how this pixel is going to distort. So due to shifting of this sensor orientation either to left side or right side, your data is going to be distorted. So we are making sure that our data should not get distorted, either it is shifting left side or right side, because you can see that if it is shifting this side, so the pixel size is going to change by this dimension. That initially at nadir your pixel size is beta times altitude of the flight, but here it is h sec of phi. This angle is going to influence your actual dimension of this thing, that your pixel will be getting distorted and you will be unable to get the exact dimension of your pixel. So those things also we are trying to compensate, and this is the typical flight line, that it is coming from inside to outside of the screen, that your this aircraft is moving from inside to outside. So if it is moving this side and your scan line is like this, so at the nadir you will be getting perfect images, but off nadir you will be not getting perfect images. So these are some of the error that you are going to get. So this is the same thing, that your ground resolution cell of this system is getting affected due to the means orientation of your satellite system, that you are using a particular scan line system to collect your data set, and that scan line system is going to distort your actual pixel size. So these are some of the problem associated with that. So if you plot this features on a planar system, so you can see that you were supposed to get your images like this. Means you can see here is that everything is a perfect square over here. Means this is a road network, this is a wetland, this is a some land parcel, there is some road network over here, and you can see that this is the line of flight. So technically you were supposed to get image like this, but due to that induced error, you can see that at this line of flight everything is getting shrinked. So this is getting compressed. You can see here is that this dimension is getting compressed. So there is a compression or shrinking in your image. So this shrinking of these images is giving your distortion to this actual features. So we are supposed to improvise these distortions in these images. Otherwise, whatever calculation you are making, suppose if you are going to compute the area of the circle, so now it is a ellipse here. Similarly, if you see this area of this square, but now it is a rectangle here, so here you will be getting a different area in compared to this area. So if it is a 1 hectare, so it is less than 1 hectare. Similarly, if you see this wetland area, so this wetland area is going to compressed here. So these are some of the real time issues that you are going to face with the data set. So in order to avoid those things, we are applying this geometrical correction. So this kind of issues will be not there in your data set. So this is the same thing, that this is a hypothetical condition, that suppose if we are going to analyze this area, and there is a cross track scanning system in your data set. So we are going to avoid this kind of system. So this kind of problem will be not there in the data set. So now coming to your external geometrical error system. So many of the time you are not aware that what kind of error may happen in your data. Like suppose you have means you are having a flight system that were supposed to fly at certain altitude, but due to some error it has dropped below that. And similarly, there is some flight system which were supposed to go in a particular direction, but there is a dip in the direction, or there is a orientation change in the direction. So in short, if there is a roll, pitch, and yaw in your acquisition system, so that will also give problem to your data set. So these are some of the external things that you have to take care in order to make your images correct one. So many of the time your altitude of your system will change. Due to that, your scale of your data set will change. So if your scale of data set is changing due to drop in the height, so you can think of that what kind of error may happen in the data set. So many of the time, due to change in the altitude of the system also, your data set is going to get get affected. So you can see here that there is a relationship between this diameter and the field of view. So if means dimension of the pixel, so if field of view is changing, so it is directly multiplied to the height of this thing. So if this height is changing, so field of view will also change, and that will affect your dimension of your pixel or a spatial resolution of the data set. So that is also going to give a error in the data set, because if you are planning to get your data set at 5 meter pixel, and for that you have elevated your satellite at 900 kilometer, and if your satellite has dropped to 800 kilometers, so due to drop in 100 kilometer, this dimension of the pixel will also change, because this field of view is also going to change. So this is some of the things that you need to take care. So these are some of the things that typically we are doing in the case of your pre-processing part: sensor calibration, geometric correction, geo registration with warping, atmospheric correction. So I'm more interested in geo registration and warping and geometric correction. So those things also I will show you that how we are going to perform those things. So typically you can see that suppose if there is a flying system, so there may be a roll in this system that it can roll clockwise or anti-clockwise. So due to that roll over this axis also, this system is going to give disturbance to your data set. Similarly, it may yaw also in the system. So due to that also we are going to get some kind of this thing, and there may be a pitch, means deep, either it may dip from this side or this side it may dip. So due to that also you are going to get a distortion in your data set. So those distortion has to be removed. So you can see that this is a distorted image of a area that in this image you can see that due to that roll, pitch, and yaw effect, you can see that there is a shrinking of this line. Are you able to see this thing? I think it is more visible that there is a shrinking of this actual feature, that how this feature is getting shrinked due to this geometrical distortion. Now once we are correcting this thing, so you can see that how nicely it is coming up. So at the edges we are getting this compressions, but in this earlier image you will not get any compression at the edge. So it is perfectly a rectangular scene, but if you process this image, so you will get image like this. But at the edges, as we have processed these images, so you can see that everything is coming perfect. This lines is perfect, this all the features is coming nicely. So this kind of things we are going to apply in order to make our data set more clear. So these are coming due to the problem of this thing. So if we see in terms of our geometrical properties of the data set, so you can see here is that suppose your satellite system or your aircraft was supposed to fly like this with a more stable thing. So nominally you will get image like this. Okay. And your decrease in altitude, as I said you, that will give a scale like this. You are able to see that your scale is getting increased here. Means your data set is more clear in compared to that. So if there is a drop in your elevation of the platform, so due to that you are getting more nice images. And if there is an increase in the altitude, you can see that your size of the pixel is getting reduced over here. So these are the three conditions that at normal case, if your satellite is flying at the planned height, so your data will be coming like this. If there is a decrease in altitude, so your data size is going to increase in terms of your pixel dimension, spatial resolution will increase. And if it is going beyond your targeted elevation, your pixel size will reduce, and it will compress your data set like this. So this is one condition you can see with help of this diagram. Similarly, if you see here is that suppose one aircraft is there and there is a roll in this aircraft like this, either this side or this side. So you can see that there will be compression in one side and there will be expansion in one side. So nominally your data was supposed to be captured like this, but due to this role in the system, there will be compression in this side and there will be expansion in this side. Similarly, if it is happening reverse side, means if your wings are rolling this side, so in that case there will be compression in this side and there will be expansion in this side, because you know that if there is a roll in the system leftward, so in that case this will become more closer to the ground, and due to becoming more closer to the ground, your data will be getting compressed here, and this will become more away from the ground. Due to this thing, you can see that this will be becoming more closer to this ground, and due to that there will be force shortening of your feature, and here it is getting elongated. Due to that, you are getting expansion in the system. Similarly, the in the reverse side, if it is rolling to right side, this will be more closer to the ground, and this will be more away from the ground. So due to that also, you can see here is that there will be disturbance in these pixels. Similarly, if you see this pitch, means either this is dipping from front side or back side. So if it is happening from nose, no, means, so it will be known as nose down, and due to that this side will be getting compressed and this will be getting means expanded, like left and right side what we are able to see in this roll type. So similarly the same thing will happen in the pitch side also, that front side will be getting compressed and back side will be getting expanded. Similarly, if it is having reverse type, means if back side is getting dipped and front side is getting elevated, so in that case also this will be getting compressed and this will be getting expanded. Similarly, if there is a yaw in the system, so if it is rolling on the axis either clockwise or anti-clockwise, so this will tilt the geometry of the frame. So typically your image was supposed to be captured like this, so now the frame will orient like this. So these are some kind of errors that you can see over here, is that either there is a change in elevation that will also affect your image. If there is a change in flight direction, that will also change your image property. If there is a pitch in the system, that will also change the type of your imaging system, and if there is a rotation in the axis also, that will also going to change. So these are some of the explanation that I have already told you, that satellite platform are usually stable because they are not buffeted by the atmospheric turbulence or wind. Conversely, suborbital aircraft must constantly contend with the atmospheric updraft, downdraft, headwinds, tailwinds, and crosswind when collecting remote sensor dataset. So here they are trying to say is that most of the time your satellite platform is treated more stable, but many of the time even your satellite system is going to give this kind of errors because you don't know that what will happen in that atmospheric system. So due to that disturbance in the atmospheric system also, this kind of error may happen. But we are means going to do similar kind of correction even for your satellite platform also. So in the case of your satellite platform also, the similar kind of things will be happening. So either your elevation will drop or increase, either your roll and pitch will be there in the satellite system, either your yaw will be there in the satellite system, and the similar kind of problem it is going to give in the case of your geometrical properties. So this geometrical properties is going to be get disturbed, and we are supposed to modify this geometrical property. Otherwise the calculation and the data set what we are going to get out of this is it will be difficult to interpret anything. So now coming to this ground control point. So many of the time, in order to means make our data set more appropriate for our analysis, we are using certain ground control point to make our data set more precise and clear. So in those cases, what we are doing is that we are typically going to identify certain road junctions or permanent features on the satellite image, and the same feature we are going to go on we are going to the ground and we are collecting with the help of GPS. So if there is a change in that point, in case of your satellite image and the GPS collected data set, so those compensation can be made to this thing. So typically we are going to collect 20 GCPs for a typical uh, satellite scene, and we are trying to transfer those ground collected point to your satellite data set in order to make our data set more clear. So there will be no problem in the case of your data set. So typically we are going to perform this geometric correction to your data set, so there will be no error in your data set what you are going to use for different application. So typically what we are going to do is that in order to make your data set more geometrically correct, we are going to make is image to map rectification, and many of the time we are going to make image to image registration process also. So we will see that what kind of things is happening in the case of your uh, this kind of error. So typically you know that many of the case you are having systematic error, many of the case you are having unsystematic error. So in the case of this the non unsystematic error, we are going to apply this kind of method. Means typically we are going to apply this geometrical correction method because we are not aware of the error that has came into the data, and we are supposed to modify those kind of error in the data set. So typically we will use this two method to correct our data set, so the data set will become more useful for different application, and we will perform this image to map rectification, and later on we will perform this image to image registration thing, and we will see that what kind of error has to be removed and how we can remove those kind of error in the data set. So those things we will see. So we will see each one of the method in precise detail that how we are going to perform this thing. So typically, means in the case of your image to map rectification, in that case we are having one topo set with us, and that topo set is geometrically corrected with us. And even though we are having problem with your satellite acquired data set, so we are trying to transfer this GCPs of your means image to this map. Means you are having a known source of your data set with you, and from this known source of data set with you, you are going to modify the unknown source of the data set. So this is the basic principle what we are going to do in the case of image to map rectification. We are trying to rectify the map uh, or we are trying to rectify the image depending on our means depending on our requirement. So many of the time your data will be having insufficient with you, so in those cases we are going to capture some of the GCP ground control point from the ground, and we will try to transfer those GCP from ground to the image or ground to the map, so your data set will become more accurate. So like that we will do. So you can see here is that one example is that, so suppose you are having means two data set with you. One is topo set is there with you, and one is your satellite acquired data set you. So we are trying to transfer this ground control point from this topographic state to this map. Means in earlier days we were not getting rectified images like what you are getting nowadays, that you are having coordinate system to your satellite images. Earlier days your satellite images were just like your JPG image, like what you are getting from your normal camera phone. So your earlier means older days satellite images doesn't have any coordinate system. So we need to give a coordinate system, or we need to give this uh, corrections to your satellite images. So in those cases what we were doing is that we were scanning our topographic sheet, and after scanning those topographic sheet, we were doing the rectification of this topographic sheet. So after performing this rectification, the same rectified topo sheet was used to give coordinate system to this satellite acquired images. So initially the satellite acquired images doesn't have any coordinate system, so we will see the common places of interest in both the images, and which is visible in both the images. So typically we try to take this road junction, so those are permanent feature and those are not going to change. So you can see here is that typically in this image also they have taken this road junction. So this road junction is being marked on this images and on this image also. So after that, the coordinate of this image is transferred to this, so that all the error that is there in this satellite acquired data set will be removed from this image, and we will be able to use this image for different application. So we are trying to take ground control point on this uh, means ground control point from this map, and we are trying to transfer this ground control point of this map to this image. So like that we are going to do, so that our data set will become more accurate, and we are means we will be able to use this data set for different application. Because in order to use this data set has to be corrected geometrically error free, otherwise we will be unable to do that thing. But many of the time, instead of map, we can use two different images also to 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 do this correction. So in this case, what we have done is that we have taken a map, means topographic map, and from this topographic map we are trying to rectify, or we are trying to geometrically correct our satellite images. But in other case, what thing will be that instead of this one image, there may be two images. Suppose there is a temporal image of the same area for two dates. So for one date we are having this coordinate, for other date we are not having this coordinate. So in that case, what we'll be doing is that we will be trying to transfer one, means earlier date coordinate system to the latest date coordinate system. So in that case, it will be known as image to image rectification. So there will be three method of this geometrical correction. One is image to map, then image to image, and third one is your hybrid. In hybrid, what we are doing is that we are taking help of both this system. We are taking help of this map also, and we are taking help of this image also to correct a third image. So these are typical things that we are ensuring in order to make this kind of corrections to these images. Because in typical remote sensing system, many of the time we are getting different kind of error, so we need to remove those kind of errors. So you can see that in this hybrid system, image to image hybrid rectification, we have taken the common GCPs in both these images. And first, what we have done is that we have transferred this GCP from rectified image to unrectified image, and later on we have cross-checked with GCP with the help of your map also. Means we have done two label of your accuracy check, that whether this newly rectified image is matching with the map of that particular area or not. So that there will be very low or very minimal error in the data set. So typically it is suggested to use this hybrid method of this geometrical correction or image rectification. But nowadays in current date satellite system, so everything is taken care by the processing part itself, and we are not doing any kind of correction. We are directly getting these processed images. So all the data set is geo-referenced and geo-rectified, and without any trouble we are going to use this kind of data set. So these are some of the things that how we are going to perform this images. So one thing is that many of the time we are going to input or output mapping logic is there in order to rectify our image. So in this case, you can see that we are giving a input from a original image to a rectified output image. Means we are trying to transfer this input from known image to unknown image. So like that we are trying to do. Another method is a inverse method, means output input. From output image we are trying to reach to the input image. Means we know that this is a rectified image, and from the rectified image we are trying to reach that in original image where this location is. So it is more related to this earlier part what I am telling you, that from image to map rectification we are trying to transfer the coordinate of map to the image. So this is the forward system you can see here is that. So logic is that we are trying to uh, forward the coordinate of your map to this image. And in case of your image to image or hybrid, we are trying to do the reverse thing, means from rectified image we are trying to validate with the help of map that whether the coordinate whatever we have transferred from image one image to other image is matching with the map or not. So these are two method of your mapping logic that is being used in the case of your geometrical correction, that we are trying to validate that whatever geometrical correction we have made is perfectly fine or not. So these are some of the things associated with that. So now coming to the application part of your that data set whatever we have seen till now. So you know that remote sensing is a combination of different domains starting from physical sciences, biological sciences, or social sciences. Means there is no field in the science domain where you cannot apply this remote sensing. So you can see that if you see the core of this part, so it typically includes three things. One is remote sensing, one is GIS, one is cartography. So in case of geometrical thing, we are more interested to see these two parts, that cartography and surveying thing and GIS thing, because this thing cannot work without performing a perfect geometrical correction to your data set. So we will see some of the example that how we are going to implement in real time scenario. So one example you can see here from the urban planning and regional planning perspective, that suppose if you are going to do the mapping and updation of the city map. So in that case, if you are not having the perfect means a perfect geometrical correction, you can think of that even though this building size may be 100 hectares of land, but it will show differently in your image. Means you can see here is that I have circled something here. So even though this area was supposed to be shown like this, but if there is a error in your data set, so it will show something empty like this. So it will be totally different kind of perspective that you will be getting in the data set. Similarly, in the case of sprawl monitoring also, that uh, if you are quantifying that how much area has grown over a period of time, and if your geometrically corrected data set is not there, so in that case also the quantification will be wrong. So those kind of issues will be there in the case of your sprawl monitoring also. Similarly, in the case of town planning, that suppose if you wish to make new township in a certain area, and if your dimensions are not correct, in those cases, even though you are going to utilize 1,000 acres of land, but on the ground it will be 900 acres or it may be 1,200 acres. So due to this geometrical error also, this kind of issues may happen. And in the case of facility management also, suppose if some vendor is supposed to lay a gas pipeline of 1 kilometer, and if there is geometrical error in the data set, so by mistake they may compute that 1 kilometer as 1.5 kilometer, and unnecessarily you will be paying extra money for 0.5 kilometer of laying of that particular gas pipeline. Similarly, in case of GIS database development also, that suppose for a city, if you are going to make a database in terms of road junction, in terms of electrical network, in terms of your gas pipeline, and if you are having inaccuracy in the data set, so in those cases also you will be making a wrong database and you'll be unable to perform any analysis out of it. So the major benefit that you are going to get after utilizing this data set is that you will be getting a better decision support system for planning and management of your uh, available data set or available services in your particular system. Similarly, it will also give a very rapid information updation system, that even there is a slight change in the height of a building in that urban area, so that will be easily monitored if you are having a very precise geometrically corrected data set. Suppose there is a government norms of making building height up to 20 meter, But if some fellow has raised the building up to 25 meters, so you can easily quantify that 5 meter extra he has raised that building. So those kind of monitoring can may also happen. So these are some of the application from the urban domain that we can apply from urban, even in agriculture also. Suppose there is a land parcel. In land parcel, if you wish to quantify that how much aggregate will be there at the end of the season, so if you are having a correct geometrically correct data set, so based on the different productivity models of that agriculture yield, we can always forecast for the future yield how much yield will be there from that land parcel. Similarly, in the case of your orchid means orchard monitoring also, that you can always quantify that how much this thing yield will be there at the end of the season. And similarly, it may also help in monitoring that what kind of uh, seasonal changes there uh, to a particular crop, because many of the time due to seasonal change also your crop is getting damaged, your crop is getting recovered. So those will also help you out to do a perfect analysis of the agriculture produce of a particular area. And similarly, coming to your forestry application also, that many of the time we are seeing that there are certain kind of decline of the forest area. So we can precisely quantify that how much area may be degraded and how much area is going to be converted from land use, means forest land use type, to your agriculture land use, from agriculture to your urban land use. So those kind of things are happening in various scenarios. So we are able to monitor this kind of thing with precise detail if you are having a more corrected data set with you. Otherwise it may lead to different kind of litigations and error, because in practical scenario, even there is a shift of 1 centimeter boundary in real time scenario, so that may give rise to multiple kind of problems to the system as well as the services whatever is being provided in that particular area. So these are some of the current research area where I am working. So I will show some of the result from that also. That currently, as I said you, that I am working in landscape analysis. So for that, I have taken uh, opposite of 1 is to 50,000 scale. I have taken the optical data of list 4, Sentinel 2, and Landsat 8, and I have also taken some of the socioeconomic data set to validate my result, and I have captured this all this incentive data set with handheld GPS, and some of the photograph I have collected with this digital camera, and I have also used this thermal infrared thermometer. So these are some of the results that I will be showing you. So for Delhi, I have worked with this urban impervious surface area, that I have tried to quantify that how much area is there in different sectors of Delhi, in different districts of Delhi, using different machine learning algorithm. So typically, I've used this supervised and unsupervised method to quantify this area, and I have validated the accuracy of this classification as well as the dimensions of this classification with the help of corresponding images also, and with the help of GPS location also. As I said you, that if you are having a geometrical error in the data set, so that can be reduced with the help of your GCPs or ground control point. So here I have done the same thing, that I have taken a satellite image. From the satellite image, I have uh, done this classification, and after performing this classification, I have validated with the corresponding satellite images, and after validating with the corresponding satellite images, I have also cross-checked the same thing with the help of GCPs. So these are some of the result of the different zones of Delhi. So these are some of the real-time example where we can apply this the knowledge of geometrical correction method or geometrical error, that if you are going to implement in the practical scenario, so this kind of issues will be there, that if you are not able to uh, do the means the proper correction of the images, so even these dimensions will be giving different in this thing. So even in this image also you can see that even though it is a corrected image, but still there is a certain issues with the classification, because the data set is having different kind of error, radiometric errors. Sometimes it may have geometric errors. So due to this geometry also, you can see that in this case also, due to the geometry of the building, everything is looking like similar. So I have to go for the field check or field validation to collect this ground control point, that where there are certain issues, so I can modify this classification. So this kind of issues are there in the urban scenario also. So these are some of the GCPs. You can see that I have collected some of the GCPs. So these are the location of the GCPs where we are going to validate our result, that whether the result are perfectly working or not. Similarly, the similar kind of application I have done with the help of radar dataset. So you know that in radar system we are having different kind of trouble in the dataset, but still we were able to do those kind of things. So for the same also, I have taken different areas, some water body I have taken, some urban cluster I have taken, some bridge structure I have taken, and I have also taken some case study of airport in the area. And I have taken some of the playground area also to validate my result, that whether the geometry what I'm able to see through this Google Earth images. You can see that there are certain geometry that will be shown with the help of Google Earth images is working fine with the radar image or not. So like that I have tried to validate. So you can see that. So this is the real geometry of your exact shape. So the exact shape, whether I'm able to identify with the help of radar property or not. So like that I have tried to quantify with the help of backscatter value. So you can see that if you see this real time Google Earth image, so it is just like different shape you are getting at the center. You are not able to identify the partition between these surfaces, but in the radar image you can see that how nicely it is coming up. So whenever we are going to quantify this water body, so this image will be helpful for me, and this image will be not that much of helpful for me, even though this image is a Google Earth image and it is nicely shown. So many of the time you can see that due to this geometry also, you can see that there is a hedginess in the image. So this hedginess in the image is giving problem to my interpretation skill. So whenever I'm going to quantify this thing, so that is also going to influence here. So for that I will prefer to use this microwave images here. Similarly, in the case of this a small water body that is in lake structure, you can see, so here also due to turbidity many of the things are not that much of clear, but in the radar image it is easily highlighted with more prominence. Similarly, in the case of urban structure, as I said you, that it is too much clumsy. That this is the urban cluster one side. This is the urban cluster other side. It is mixed with the urban and green cluster that is being shown in the Google Earth image. But in the radar, uh, here also I'm having that trouble. I am unable to identify. So you can think of the issues that will be associated with the geometry of this images. So even though if I say you to quantify the building dimension, it will not possible for anyone to quantify this thing. So this is the real time problem that we are getting in the case of our satellite system. Similarly, in this image, even though I was not able to identify the road, but in radar image I am able to identify this road. You can see this road is nicely shown in this radar images. This road is easily depicted in the radar images. So many of the time your parallel images will be helpful for you to identify these features, but many of the time it may not work nicely. So similarly for uh, this bridges also, that here I have taken two bridges. One is iron bridge, one is a concrete bridge. So you can see that how this iron and concrete bridge is uh, getting depicted in this radar images. So in the case of this concrete bridge, I'm not getting that much of prominent illuminance in the radar images, but in the case of my iron structure, it is coming nicely with good illumination. That is happening due to nice back scattering that I am getting from the iron structures kind of thing. So these are some of the things that are associated with the help of that are associated with the feature type also, that if it is a concrete structure, the illuminance or the scattering that you are getting from that structure will be different. If it is a kind of metallic structure, the backscatter will be different. So these are some of the things that are associated. Similarly, if you see the airport area, that this is the real time uh, seen from the Google Earth images. And if you see the same thing from the radar image, so it is nicely depicted in the radar image. So if someone is interested to uh, do the geometrical analysis of the different road network, so it is easier for me to identify the geometrical structure of the road network. But in the case of your this Google Earth image, that is not nicely shown over here, so it is getting dissolved with some other feature, but here it is nicely shown. So it depends on the application, that in which application we are going to apply our different images. So even in this airport structure, you can see that we are unable to identify this clear view of this road structure, but here we are able to identify the clear view of this uh, runway and other road corresponding road structures. So those are some of the things that are associated with the geometry of this thing. Similarly, if you see the playground area also, this is the real scenario of the playground area, but in the radar image somehow we are able to get the structure, but here it is not nicely shown. And similarly for this uh, means central this grass is there, so that is not nicely depicted. So for some feature you will be getting a good identification, but here also it is difficult for us to quantify the dimension, that even though we are able to means digitize with the help of certain tools, but here also we will be getting certain kind of error. And in this case also you will see that even though you are getting this proper shape of this covering of this uh, stadium, but if you wish to quantify this complete area, so it will be difficult for you. So for that, even we have tried with radar images, so there also the same issue is there. So that's it from my side. Thank you.
Thanks, Dr. Deepak, for excellent presentation. Now I will ask the participants that in case they have got any question, the house is open for discussion. Anyone?
Uh, Sir, good morning.
Good
I want
morning.
to ask, sir, from where this radar data you have taken, sir?
So radar data set is we can collect from multiple sources. So for this particular case, I have taken this data set from Sentinel-1 archive. Either you can use Sentinel-1A or 1B.
Okay, sir. Thank you.
Hmm.
Sir, good morning, Deepak sir.
Good morning.
Sir, when you said that oblique image corrections chapter,
Yes.
in that, do we have some techniques by which we automatically can correct those images, or we need to take the images again for the corrections? Because
No,
there are
no.
two type of errors in the oblique images.
Yes.
One is the entire image is oblique,
Yes.
and second, the high-rise buildings which are coming as a oblique part in the images.
Yes.
Those hide several other features also.
Yes.
Yeah. So, is there any technique to correct those kind of specific buildings or errors?
Yes, Sunil, very nice question. First of all, I would like to apprise you. So, first part of your question is regarding your this oblique image. So, first thing is that we can use image ortho rectification, that is typically available in any one of the commercial or open source softwares. So, that tool you can
Yes.
use.
Yes.
And coming to second part of the question, that is related to shadow and hiding of the feature. So, hiding of the feature cannot be illuminated, but you can use radar images to means eliminate that hidden feature. So that is second answer. And third was regarding correction of your building heights. So typically in urban area this kind of things will be happening. So typically if you wish to quantify the dimension of the building, so we are supposed to take a ortho image. Okay, means footprint should be clearly visible, but due to this orientation of the satellite images, you might have seen that many of the satellite is oriented at certain angle, maybe 93 degree, 94 degree. So in those cases obviously we'll be getting certain shadow. Perfect perpendicular, none of the satellite is going to capture your image, you know this thing. So what we are doing here also is that we are using that ortho rectification to remove that shadow effect from your that urban area.
Yes, sir. Thank you very much for the clarification. Actually, we get so many disturbed such images in the
Yeah.
region or city like Mumbai.
Yes, yes.
So,
Even any urban area you take from either India from abroad context, you will be getting this kind of
yes, yes,
images.
yes, sir. So thank you very much, sir.
Thank you.
Good morning, sir. Sir, I have a
Morning.
question.
Yes.
Sir, how to carry out geometric correction over the ocean area where we have no ground control points?
So in that cases, nowadays we are having radar altimetry data set. So typically we are using reference of that, because there also we are having different kind of issues regarding your tide will be there, wakes in the tide will be there. So for that we are using that radar altimetry data. So for that, these are the technique till now. So apart from that, I don't think any other technique is there for those areas.
Okay, sir. Okay, thank you, sir.
Thank you.
Sir, good morning.
Good morning.
Sir, what could we use as control points in the area where there are no well defined points?
Can you give one example of that? Like, if I say that if it is a planetary surface, so in those
Yes.
cases, you can say that there will be no well defined. So in those cases, we will be taking certain reference, like pole area will be taking a reference, and sometime we will be taking certain landing site, because many of the time you know that many of the uh, time we are sending certain robots or certain kind of equipment to some unknown area, so we will take that point as a reference as a GCP, and from there we will start all the calculation.
Okay. Sir, like in desert?
Hmm. In
Uh,
desert also we have to transfer the coordinate, like what we are doing in the manual surveying thing, that each and every city is having certain known reference system. Means
mhm.
typically the railway station of any city, if it is having a railway station, so that railway station will be having a benchmark height. From that benchmark height you have to transfer the coordinate to the unknown area, like that we will be doing.
Okay. 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 So thank you.
Hmm.
Yeah, there is one question coming up
Yes.
from student, that how the microwave remote sensing will be helpful for flood forecasting and flood mapping.
Okay, so this is very means upcoming thing, and this is very much useful for flood, especially because many of the time there are certain features which are getting hidden due to the shallow flooding, especially in the urban area. If there is a flash flood and if there is a submergence of certain infrastructure, so you cannot do the survey with any other technique. So if you are using a certain microwave images, if you are using for that, so even you can identify that what is the uh, hidden structure below the shallow this flooding kind of thing. So this is one of the thing. And apart from that, if there is some emergence of crop in agriculture field, so that can also be identified, because the back scatter that you are getting from crop will be different from the back scatter that you are getting from a soil moisture area. So like that.
Thank you. And last question I'll be taking up. I will not take because they're flooded of questions. So,
No
how
problem. I'm
micro
okay with that.
uh, so how microwave remote sensing is useful for forest biomass studies?
So for the biomass studies also, that we are able to know the canopy of the tree, we are able to know the girth of the tree. So in those cases, with certain allometric equations are there, so we can transfer this thing with the help of microwave dataset, and it will be very much useful to assess those things.
So, another question: there is any indices used for this uh, kind of studies? Any
Yes,
particular
RVI
indices?
is there. Radar vegetation index is there. Like NDVI, we are having normalized difference vegetation indices. So similar manner, we are having radar vegetation indices. So those are also helpful for means some kind of you can say inference study, not exact study, but inference study we can perform with that.
Sir, this is Varun this side, sir. I have a sir
Yes.
question for this.
Yes. Hmm.
Sir, what should be the measures that should be taken into consideration while we are correcting our microwave data sets?
So in case of microwave data set, Varun, here also the same thing is there, that we have to take care of these GCPs, that wherever we are trying to transfer the GCPs from uh, our ground to, or from map to this images, so we have to take care of the permanent features. So beyond that, I don't think any other thing is there to be taken care. Like in the case of optical, it is visually appealing that you can see that where is the road junction, but in the microwave it will be difficult for you to identify that thing.
Yeah, yes, sir. That's the problem in microwave because SAR data
Mm.
sets, when we use SAR data sets, so
Mm-hmm.
it is not easy to find out some GCPs.
Yes, yes.
So can we use some reference image from optical sensor
Yes,
for?
yes. The same thing I'm saying, Varun, that you identify some permanent feature, the optical, you just overlay and you just mean visually cross check that it is the same location, like that we can do. Because you will be unable to see any feature in the radar. But in the case of your this thing, that snap, if you uh, this thing finally process the image, you can parallelly open your this image also, that Google Earth image. So like that we can do that. You can earmark that location and you can transfer like that. So that is also one possibility that we can do.
Yes, sir. Sir, actually, sometimes I face the problem while when we are using a reference image from different spatial resolution. So in that
Mhm.
case, sir, what happens? There may be some kind of shifting because uh, all the optical sensors generally we use Landsat data sets of 30-meter
Yes,
spatial resolution,
yes,
and
yes.
our microwave data sets are, if it is having good resolution, so there may be some problem to identify the exact location because of the differences in the spatial resolution, sir.
Yes, yes, I agreed. So that's why I'm saying that if you're using Sentinel series of microwave dataset, 1A or 1B, so I would suggest that use 2A, 2B. So you will not face any error with that,
Okay, okay.
because
If
that is
if
a parallel data set. So both are at 10 meter. Typically, if you process a Sentinel 1A, 1B data set, so
okay,
at the end you will be getting 10 meter of your macro data set. Typically, you will be getting like that, and 10 meter is really available from 2A, 2B. So you can parallelly geometrically correct your data set, like that we can do.
okay. So, sir, first we have to correct our Sentinel 2A 2B data sets, then we can
No,
use
no,
it
no.
for reference, or
No, 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 no. Just pre-process your Sentinel 1A, 1B, that is macro data set. No? So
yes.
you can process the data set. So at the end, you can transfer the coordinate from 2A, 2B to
Okay,
1A, 1B, like that.
okay, okay. Thank you, sir. Thanks for clarification, sir.
Hmm.
Thank you very much, sir.
Okay, well, nice question. So this kind of problem is happening in the case of radar system. So that is still under means development phase, what I feel.
Yes, sir. That's a major problem while we are using microwave data sets.
Yes, yes. The
Okay,
same thing
thank.
was there even for the optical. If you see 10 year back, the same thing was there for the optical data, but now everything is corrected.
Okay, thank you
Hmm.
very much, sir, for this clarification, sir.
Yes, yes,
Sir, I have a question, sir. My name is Bhavni Gulati, sir. Good morning.
yes.
Sir, which data set are better for T structure mapping, LIDAR or SAR data, sir?
Tree structure mapping.
Yes, sir. T
Uh,
canopy
uh,
structure types.
LiDAR will be useful more in compared to SAR, because in SAR you will be not getting that much of this thing, that accuracy. It will be getting dissolved many of the time, because you are taking from a very high platform. But in the case of LiDAR, you will be getting a with a terrestrial platform, so it will be useful more in compared to your SAR. If you are having LiDAR, you go for LiDAR.
Sir, can you suggest some LIDAR data set that we can download for free?
So LiDAR dataset, I think ISAT is one website you can try it with that. ISAT is one archive. Those are supplying this some sample data, not exactly of your area it will give, but some of the sample data it will give you.
Okay, sir. Thank you so much, sir.
So I thank Dr. Deepak that he has given a very in detail explanation to each and every participants, detailed knowledge about geometric errors, whether it's you're talking about internal, external, with applications, how the radar data sets are used for various kinds of land feature identifications and different kinds of polarization that we are using in, as well as corrections. And on behalf of Center for Climate Change and Water Research, I again Thank you that from your busy schedule you have given us the time, and all the participants and students were benefited from your talk. Thanks a lot, and we hope that you will be collaborating us. You will be supervising our students for their future research. Thanks.
Definitely, Dr. Suraj, and I do appreciate your effort in following all the things with me. That whenever is when is the lecture, whether it is done or not. So I thank you for that, all the effort what you have made to realize this lecture successful. And I do thank all the organization from bottom of my heart for giving me this opportunity to interact with the participants. So thank you all and all.
Thank you. Thank
Thank
you.
you very much, sir. Thanks a lot
Thank
for
you.
your informative lecture on this important topic in remote sensing, sir. Thank you very much, sir.
Thank you.
Deepak sir, thank you very much for
Thank
accepting
you.
our proposal
Thank you,
and
ma'am. Thank you
giving
for giving
such
me.
an informative talk on geometric corrections
Yes.
for the all the students. Thank you.
Thank you. Thank you, ma'am.
Now, Miss Priyanka, please introduce our next speaker. He has joined.
Okay, thank you, sir. Well, this was a very informative and interesting lecture altogether. So now moving forward to our next speaker, I would like to take this opportunity to give a brief introduction of our guest speaker, Dr. Ajay Kumar Tharoor. Dr. Ajay Kumar Tharoor has obtained his doctorate in remote sensing and GIS application in hydrology from Jammu University. He has over 13 years of research experience and applications in geospatial technology of natural resource management for land and water resources. He is a lifetime member of many reputed societies and organizations like European Water Resource Association, Himalayan Geology, Indian Association of Soil and Water Conservation, and many more. He is also member editorial board of Quaternary Science Advanced Elsevier, and he has many research publications and books in reputed national and international journals and publication houses. Now, I would like to invite Dr. Ajay Kumar Tharoor to take this session forward. Sir, you're most welcome. Sir, you have to unmute, sir. It is muted.
Thank you very much, Priyanka Roy.
Thank you,
My
sir.
thanks to Madam Shruti Kanga and Dr. Suraj Kumar Singh for inviting me for today's lecture on remote sensing and GIS applications in geosciences, as well as radiometric corrections. So, first I wish to interact with the participants that what is the level of the participants from which backgrounds they are comes from. So, can I interact with the participants? That what kind of levels they have
Yeah,
earned
sure, sure.
regarding the remote sensing and GIS.
Yeah,
So,
I'll be briefing about the participants. Basically, they are mixed participants. Total 27 are selected from all over India,
okay,
and few are professors, few are research scientists, PhD scholars, NGO, and I have made my students to join. They are the students of MSc and MTech Geoinformatics. So it's a mixed crowd. Somebody will be from fourth semester, somebody from fourth, somebody. So we have got a mixed crowd all together. But in general, all have the basic knowledge and the domain of GIS and remote
okay.
sensing.
So then I will directly go to the radiometric corrections, even though it's all kinds of corrections. So Suraj, is it visible now?
Yes, sir, it is visible, sir.
Okay.
Yes, sir.
Sir, could you please make it into slideshow mode, sir?
Yeah. Show full screen. Okay. Is it okay now?
Uh, so it is still in a slide presentation mode, sir.
I have to make it now full screen. I don't know why it is.
Dr.
Yes,
Ajay,
sir.
please share the entire screen. And then, because when you will share through a window many times, you even if you're doing a slideshow mode, the viewers cannot see in full
Okay.
screen. So
But I
when
have
to
made it
stop,
now the full screen. I don't know why it is not showing to you, but
so
okay.
stop it, and again re share it using entire screen option.
Okay.
Now open your slides. Open your slides.
Okay.
So we can see your now slideshow mode. Please do it. Yeah. Now we can
Okay.
see. Now
Okay.
we can see.
Okay. So today is the radiometric corrections. So I think if you have the basic knowledge of remote sensing and particularly the remote sensing, many of you already know about the radiometric corrections and what are the major errors we found during the data we got in the optical as well as thermal and microwave remote sensing. So radiometric corrections is how we measure and how we are able to get all these things. The radiance measured by any given systems over a given object is influenced by changes in the scene illumination, atmospheric condition, that what was the atmosphere at that time, whether it's a sunny weather or any other kinds of atmospheric hindrances which hinders the coverage or satellite view to take the picture. Viewing geometry variations greater in the case of airborne data collection than in a satellite image acquisitions. So instrumental response characteristics. Sometimes instrument may not behave properly as it is so such kinds of things may lead to the atmospheric and as well as radiometric errors in the data. So these are maybe due to sun elevation corrections and earth sun distance corrections and haze compensations. So all these we will discuss here. So then the noise corrections means electronic noise, both random and periodic. Sometimes any kinds of noise in the during the data acquisitions may take place randomly, or it may take at a particular period of times. Then sun angle corrections for comparison and mosaic images acquired from different time of the year. It may also lead sometimes of error. Correction of atmospheric scattering, subtract the haze digital number values from the different bands digital number. So radiometric correction addresses what? It addresses the sensor and processing effects, atmospheric effects, background absolute corrections, and some relative corrections. So as I have already told you that radiometric correction may be necessary due to variations in scene illuminations and beam geometry, atmospheric conditions, and sensors noise and response. Each of these will vary depending on the specific sensors and platform used to acquire the data and the conditions during the acquisition. So it may be desirable to convert or calibrate the data to known radiations or reflectance unit to facilitate comparison between the data. So radiometric corrections and sensor processing effects are radiometric atmospheric effects, which are backgrounds, absolute correction, relative corrections, and topographic effects. So there are two kinds of major effects we found here in the sensor and processing, that is atmospheric and topographic effects. So one of the major problems during the atmospheric or you can say any kinds of radiometric correction is the noise removal. So noise is what is noise? Is noise in image. Noise is an unwanted disturbance in image data that is due to limitations in the sensing, signal digitizations, or data recording processing. So noise comes from various ways, atmospheric as well as radiometric errors in the data. So potential source are electronic interference between the sensor components. So noise can either degrade or totally mask the true radiometric information content of a digital image. So it can be reduced up to any subsequent limits. So noise removal usually precedes any subsequent enhancement or classification of the image data. The objective is to regarding the noise removal, how we able to remove the noise. The objective is to restore an image as to close an approximation of the original scene as possible. So we try to reduce the noise from the image so that exact image what available on the surface of the Earth and what is required to get from the satellites, that we try to make a original scene as possible. So line strippings and banding is common things, which is de-stripping. So line strippings occurs due to non-identical detector response. So sometimes when the satellite tracks the surface, so these kinds of errors found in the satellite's data, which is known as line strippings. Although the detectors from all satellite sensors are carefully calibrated and matched before the launch of the satellites, but still these kinds of line stripping errors found here. With time, the response of some detector may drift to higher or lower level, resulting in a relatively higher or lower value along very fixed line in the image data. Lines stripping is corrected using the histograms per detectors. So every detector's histograms we use for line stripping corrections. So and then another kind of error is line dropout error, occurs due to recording problem when one of the detectors of the sensor is in question either gives wrong data or stop functioning. The Landsat ETM, which have a 30 meters of resolution, for example, has 16 detectors in all its band except the thermal band. A loss of one of the detector would result in every 16 scan line being a string of zeros that would plot as a black line on the image. Drop lines are normally corrected by replacing the line with the pixel values in the line above or below or with the average of the two. So what the detectors do here, component of the remote sensing systems that convert electromagnetic radiations into a recorded signal. So then atmospheric path radiance is a term that refers to that component of radiation received by the sensor that did not originate from the target but through scattering in the Earth's atmosphere. So these, if you see that these are the noise errors, even though this is the SAR-B radar image before and after the removal. So you can say this is the noise found in the image as a stripping lines. So after we correct by using the different methods for different kinds of images, likewise in the optical data we do another kinds of processing, whereas in the microwave SAR data we use another ways to remove the noise. So you can see the difference between the two images. This is the noised one, and this is after the corrections from the by using the various filters to remove the noise from the satellite data. So then stripping. So here you find here the strippings errors in the data. So after the de-stripped, you find such kinds of image as a processed one. So certain kinds of processing in the radiometric or any other kinds of error which found during the data acquisitions can be possibly reduced, but it cannot be 100% corrected image, but it can be reduced up to a certain extent that we can get a sufficient information for our analysis. So partially missing line. So these are scan lines. So you are finding here that data are not showing in a particular line here. So this is also one of the major errors even found in the Landsat 7 and 5. Some data you get to extract from the USGS Explorer. So certain kinds of lines are found in the Landsat 7 data. So strippings, like you can see here, the strippings in the band found in such a way, and these are the exaggerated portions. So stripping was very common in the earlier Landsat MSS data due to variation and drift in the response over the time of the 6 MSS detectors. The drift was different for each of the 6 detectors, causing the same brightness to be represented differently by each detector. The corrective process made a relative correction among the 6 sensors to bring their with each other. So then the line dropped. So sometimes line drop may also occur in the satellites data. So line drop occurs when there are system errors which results in missing or defective data along a scan line. So scan lines, if complete lines have been found dropped, normally lines are drop lines are corrected by replacing the lines within the pixels. Even now, in the ADAS as well as in the ArcGIS software, there is one small modules which we can plug with the ArcGIS, and these scan lines can be reduced up to a certain extent to get the better quality data. So that is specifically for the Landsat data sets. So geometric corrections addresses sensors and processing effects, atmospheric effects, then absolute corrections and relative corrections, and then topographic effects. So the direct illuminations, so we find here that how the data and got the radiance from the solar irradiance, then total radiation and the sensors and remote sensing detector. So average background and average target reflectance of a pixel of interest. So such things is made during the satellites data acquisition process. So this is the direct illumination in the scattered one. So such kinds of scattered illuminations found during the data acquisitions. So then adjacent reflectors if are there, then how the path radiance behave. Path irradiance stems from two sources, directly reflectant sunlight and diffuse skylights, which is sunlight that has been previously scattered by the atmosphere. So you can find the differences among all these things. So then the brightness value increased by the scatter, brightness value reduced by the absorptions. So if there is a scattering, the brightness value of the image increases. So it can be reduced if there is an absorption. So generally we found in the scattering mechanisms that the brightness value of the image increased up to a larger extent. Then LLK scattering caused by particle much smaller than a wavelength, declined with the fourth power of the wavelength. So responsible for blue skies, red sunset, key elements in the radiometric corrections of the image. So such kinds of LLK scattering is found there. So some forms of radiometric correction is required so as to be able to more readily compare image collected from different sensors at different dates or times, or to mosaic multiple images from a single sensor. So sometimes all these kinds of corrections are very much required when you have a data from the different source to mosaic them. So absolute radiometric correction is analytically approach to driving reflectance values from a raw digital numbers, dn to radiance, and then radiance to apparent reflectance to ground reflectance. So I think the digital numbers, you all know that how the digital number we got from the solar radiance. So it is a function of reflectance of the target material, solar distance, atmospheric scattering and absorption, slope and aspects of the reflecting surfaces relative to solar azimuth, angle of viewing of the sensor relative to the local terrain orientation, gain setting of the sensor. Then absolute corrections we made here in such a way that convert D into radiance lap, sensor dependent, which is Laplace filter. So pixel apparent radiance L, then apparent reflectance, then ground target reflectance. So in such way, even though the many other methods are found, where we not absolutely but up to a certain extent, the radiometric corrections can be found. So then Landsat ETM plus digital number to radiance, L is equal to gain into digital number plus offset. So spectral radiance measured over the spectral width of the channel, then the minimum radiance required to generate the maximum digital number. In case of 8-bit data, it is 255, and then the minimum response is 0. So as it is 0 to 255, the digital number value, then G is the slope response function, and the intercept of the response function, that is channel offset. So in such way we are able to get all these things. So then the L max and spectral radiance and minimum. So digital number from 0, 1 to 255, such kinds of gainings can be made. So The apparent radiance measures effects. I think I have just to taught you the radiometric corrections. So even though these are also part of all these things, the atmospheric effects we have found that the apparent radiance measured by sensors, then the reflectance of the object atmospheric transmittance is radiance on object incoming, and then alpha is the path radiance. So the apparent radiance measured by the sensors, so that is reflectance of the object into atmospheric transmittance into radiance upon plus LP, so which is the path radiance. So this way we are able to get all these things. So then sun angles corrections, so, sometimes it also found as a cause of atmospheric errors. So position of the sun relative to the earth changes depending on the time of the day and day of the year. Then solar elevation angle, time and location dependent. It is in the northern hemisphere, the solar elevation angle is smaller in winter than in summer. The solar zenith angle is equal to the 90° minus the solar elevation angle. Impedance varies with the solar changes in solar elevation angle and changing distance between the earth and sun. So that is digital number corrections is equal to size of the angle is given in the header of the image data, that is a digital number upon sine alpha, and absolute correction involves what it involves in the dividing dn value in the image data by the sine of the solar elevation angle. So you can find that the corrected image, this is the error1 image, and after the corrections, so you find here that the image is corrected to a sufficient base. The left is image is acquired at sun elevation of 37 angle, and right one is acquired at 42 angle. So you can find that the sun angle also is the important factors during the image acquisition or the data acquisition process. So these are the bands by which the spectral irritance value can be stored. Then haze reduction, sometimes haze is also one of the reasons in the atmosphere. So aerial and satellite image often contain haze. Presence of haze reduce image contrast and make visual examination of image difficult. Due to ray scattering, particle size responsible for effects smaller than the radiation wavelength, that is oxygen and nitrogen. Haze has an additive effect resulting in higher dn values. Scattering is wavelength dependent. Scattering is more pronounced in shorter wavelength and negligible in the near infrared region. So if you get any image during the winter seasons in the northern India, so haze is one of the major issue. I will get the data from August to February for the northern India. So most of the time you will find the haze in the data sets of Landsat series of satellites. So haze reduction means one means of haze compensation is multispectral data is to absorb the radiance recorded over a target areas of zero reflectance. For example, the reflectance of the deep clear water is zero in NIR region of the spectrum. Therefore, any signal observed over such an area represents the path radiance. This value can be subtracted from all of the pixels in that band. So in such way, so target reflectance into atmospheric transmittance into incident solar radiance into path radiance. So in such way, we are able to get the haze reductions. So you can see that before the haze removal, the images look like this way, and after the haze removal, we'll get not very clear image, but up to some extent we are able to get some kinds of information from the data sets. So this is also the haze. One is the haze image, and another is the corrected one. Even though data is not so much correct of good quality, although sufficient improvement have been made in this data set. So this is the aerial image of hazy, and after the haze removal, you can get that how much clear the quality of the image is. So this is the end of atmospheric and radiometric corrections presentations. So now the next presentations is related to the, so I am stopping this one. And the next slide is
Dr. Ajay, there is a question from one of the students regarding the
shall I take the questions after the completion of both the slides or take it simultaneously?
Depends on you, as you
I
direct.
think I'll take the questions after the completion of that one PPT also.
Okay. So Sunil, please, and other participants, do write your question on a paper and pen,
Okay.
and it will be taken once the entire presentation is done. Sir, please.
Is it visible now?
Yes.
Okay. So this one presentation is remote sensing applications in the geosciences. So geosciences is quite broad subjects, and application is remote sensing applications in geosciences are more than any other kinds of science. Geosciences has too much applications, right from the oil explorations to geohazards, natural hazards, avalanches, then tectonic kinds of analysis. So if we'll mainly think about that, how a young researchers can start working in the geosciences research. So I am showing here some basic things. Then what I have done in the last 5 years. Then I'll show that slides. So if you see, look at this satellite data of Landsat 8, this image belongs to the Dehradun area. So we find here. So the slide is showing to you. Is it in the changing mode? Hello?
Sir, it is not yet in slideshow mode, sir.
Slideshow mode.
Okay.
Open your slides. You can see. नहीं यहाँ से नहीं, यहाँ नीचे बस आप ओपन अपना स्लाइड्स खोल दो, दिख जाएगा स्क्रीन पे. हाँ. वो स्लाइड शो आप स्लाइड खोल लीजिए और इसमें कर दीजिए वो प्रेजेंटेशन मोड, तो दिख जाएगी. हाँ जी.
दिख रही है? अभी दिख रहा? हेलो सूरज जी.
हाँ जी दिख रहा है सर, दिख रहा है सर.
चेंज हुआ?
हाँ.
Okay then. So as this image satellite data of Landsat 8 belongs to the Dehradun area, so we find it as geology means the what lies on the surface of the earth. So geosciences means the science of the surface or rocks, you can say. But what lies beneath the surface of the earth, we are also able to get from the surface features. So if you look at here, so you find here that all the drainage channels have been shifted up to a certain extent. So if I draw here a one line, so I will find here that something has happened below the surface. That's why all these drainage have been shifted up to a certain extent. Same way here also. So you will find that small shift of the drainage having taken place. So if I look at here also, then I'll see that drainage are shifted at a particular trends in a way that something has happened here. Likewise, here also. So this means that some geological activities have been taking place below the surface of the earth. So in such a way, we are able to mark here certain kinds of faults or lineaments so that we are able to analyze what lies beneath the surface of the earth. So satellite image provides more than sufficient information about the earth surface as well as below the surface of the earth in terms of geology. So what we'll do in terms of geosciences, that the first and the basic things we study generally in geosciences, the watershed kinds of studies, that if you have a geohydrological units which drains into a singulate output, likewise in this case that you have a drainage and your water is moving out of there, which is known as the pole point. So in the geology, we try to make certain kinds of analysis whether this kind of watershed or if the area is very much large and if it is tectonically active or not. So such kinds of tectonic analysis we make from the satellite. So this is very simple for you, that how will you delineate the watershed. Even though nowadays the watershed is delineated by using the digital elevation models. So any kinds of data from them you can delineate your watershed, and then on watershed you can make certain kinds of analysis. Likewise here, these are the contour lines, and this is the digital elevations model, so which showing the elevations, and this is the satellite data. So here also you can find that the rivers are moving, and this is the core point of any drainage basins. So these are the selected drainage and streams. So even from here also, we find here that drainage are taking a sinistral bands at a particular locations. So this means that something has happened below the surface of the earth. That's why the earth have the drainage have been shifted at a particular patterns. So this is the classification units, as I'm telling you that if you have a watershed, whether you have a catchment or sub-catchment. So these, even though above the catchment, if your area is more than 500 lakhs of hectares, you can say it's as a basins. So if I will work on the morphotectonic analysis, which is very basic and important part of any kind of research in the geosciences. From the morphotectonic, we are able to analyze whether tectonic activities have been taken place in your area of interest or not, whether any kinds of crustal deformations is going there, or many kinds of analyses from the satellite images related to the morphotectonic analysis we can make. So this particular image, what I have made, this belongs to the Gagas basins in the Uttarakhand. So this is the shaded relief digital model, which is shown below, and in the shaded relief, I have marked certain geomorphological features. So you can see that geomorphological features have been marked here, and then name of the villages, then terraces of the rivers. If someone, many of you I think belongs to the geosciences or earth sciences, like from geography and geology background, so they able to know that these are the terraces, that T0, T1, T2 and T3. So having marked along the river channels. So then I have marked here the North Almora thrust. Okay. So likewise in the right one figures, I have marked here certain kinds of fault based on the shifting of the rivers at a particular distance. Okay. So here rivers have been taken a band, so I have marked this fault as FF. Then here many faults have been marked. So when I plotted them in a 2D profile by using the digital, by using the spatial analysis in the ADAS Imagine or any other kinds of, even though you can use the Saga software. From the Saga software, you can make a 2D profile. So these 2D profiles which I have made, it also showing that certain kinds of changes in the slope have been taken place. So based on the digital elevation models, I have made the nick points. So these nick points have been generated from the digital elevation model data, so which are clearly showing here. So this one, the Karchuli fault is this one, and this one is the Koyura fault is this, and Medidla fault here. So it is also showing certain abutment, and here also displacement along the net is shown. Then in the Sukhadevi fault, this is the Sukhadevi fault. So if we plot the digital elevation data by using the spatial analysis, we are able to plot all these kinds of faults along the 2D, which is showing that something has happened below the surface of the earth. What happened below the surface of the earth, that is a secondary question. But if we are able to get from the satellite data, that is optical data, as well as from the digital elevation model data, so we can plot in such a way. So this is also the part of the last mason. So you can see that how much shifting of the rivers have been taken place. So the river is shifting in this way. So here we have marked one fault that this portion has been displaced to the right place, and this upper one has displaced to the left place. So we have tried to develop an idea that here our shutter which have been developed, and this portion was earlier part of the value channel, and due to blockage here at Tortuga, the value lake have been formed, and which was busted after a period of time, and the value sediments, or you can say the fluvial deposits, have been deposited here. And even though nowadays, also when I visited in this particular area, I find that such kinds of poker village sand ponds have been found there. So these sand ponds are earlier part of the major paleo lakes in this area. So satellites help us know that what happened in the earlier periods, so we can develop an idea regarding that. So then various kinds of morphom tectonic indices which we are able to get from the satellite data. So this is the stream length gradient anomalies we have plotted for the various watersheds. So this is GVW1. For this particular watershed, we have find that such kinds of displacements have been taken there. So right from GVW1 to GVW11, we have made all the elevation and spatial midpoints marking. So you can find that high peaks to the topographic peaks are, you can say, midpoints are recorded in the middle and lower reaches of all the last basin watershed. Whereas in the upper reaches shows there is no prominent peaks except watershed 1, 2, 7, and 11. 1, 2, 7, and 11, there is no major peaks in the lower reaches. So you find here that in the lower reaches, this is from the upper to lower reaches. So here you have a high peak in the 1, here high peak, in the 2 high peak, here we don't get any kinds of high peak. So these things help us to know that whether any kinds of tectonic activity or deformations have been taken over the period of time or not. So I think this is for you. So slope, we all know, so slope is one of the major factors in the topographic locations. So slopes helps us know the many things. So if how you measure the slope, this is the classifications that slope calculation is H upon D, this is H and D. We got the slope percentage. So another study we have performed in the Drumdrum basins of the Janskar Himalayas. So this is the Drumdrum basins. So in the Drumdrum basins we have developed this, and we found that here something has happened. So we find marked here as a fault. These are the info fault. We have not gone to this area, but based on the satellite data, this one is the Google data. Based on the Google data, we have tried to mark here the fault, because river have taken a strong shift. So based on the shifting of the rivers, we are able to get the faults here. Because rivers tells us what lies beneath the surface of the earth. So in the same way, we have marked here the different watershed regarding the river basins. This is the geomorphology map. And then by using this Google data, we try to make the certain mountain front seniority, means the front of the mountains. So based on the mountain fronts, we are able to determine that whether it's tectonically active or not. So mountain front seniority is also a kind of very important indices which helps us to know whether our area is tectonically active or not. So reflectance, a balance between the tendency of a steam and slow process to produce irregular mountain fronts, and vertically active tectonic that tends to produce a more prominent straight front. So based on the value, if this mountain front is value is 1, it means it's tectonically active. It's less than 1, then it is less tectonic. If it is more than 1.4, then tectonically active. It is slightly active if it is 1.4 to 3, and more than 3 it is inactive settings. So how we determine this mountain front seniority? So we determines it that LMF, this means straight line distance along a contour lines. So this is the straight line distance for any mountain front, and then LS is the true distance along the same contour line. So based on that, we are able to get that whether our area is tectonically active or not. So this is the another study area, that is the Vilangana basin in the Uttarakhand Himalaya. So we have taken the 2 rivers, that is one is Mandakini and another is Vilangana. So based on this particular basins, we have also made the tectonic or morphotectonics analysis. So you find here, okay. So this one is for the block basins. So right here, so another analysis for the drainage basin, whether it's asymmetric basins or asymmetric basins, because symmetry and asymmetry also helps us to know whether it is tectonically active or inactive. So for both the basins, we have determines this basin's asymmetry factors, and we are able to determine that which watershed in these 2 basins are active and which one is inactive. So we find here and prepare a map that if AF is less than 5, that is inactive basins. So we find that these are inactive, and if it is more than 15, that is most active basins. So inactive and active settings we are able to develop from there. So it determines from in this way that AR is the straight line difference and AT is the distance in the tilted way. So in the same way, transverse topographic symmetric factors, the T applies the amount of asymmetry of a stream within the catchment and variation of the symmetry in different segments of the valley. The middle of the drainage basin would be the location of the stream. So from the middle of the stream, for any particular watersheds, we try to measure the length, and then we are able to get, if the T is equal to 0, then it is symmetric basins, and if T is more than 0, then it is asymmetric basin. So if it is asymmetric, then that means that basins have been shifted or drifted to some base. Then another issue is the ratio of valley flow to valley width to valley height, ratio of valley flow width to valley width height. So this can be determined by using the DEM data, by using the formula 2BFW into EIA minus ESC. This is the right hand side, or the width of the valley flow, and elevations of the right hand and left hand sides of the valley flow, by which we are able to get that whether our basins is implied to differentiate. Basically, here we generally get that whether it's a U-shaped or V-shaped valley, because if it's a U-shaped valley, that means that has been derived from the glaciers, and if it is V-shaped, that means it's derived from the river course. So by such way, we are able to get the information about the river tectonics. Then another study which we have made in the Sondun basins. Sondon is lies just above the Chandigarh. So uh, this is the study area we have taken. So here we have a Janori anticlines. These are the mountains, and here also we have the Lesser Himalayas. You can there are stone thrust is found there. So here a Satluj river is moving. So on the Satluj river, whether this portion, which is the valley filled area, is active or not active. So in this particular study area, we made a RIAT, or you can say the deformation kinds of analysis. What we have earlier, I have told you that groundwater prospect potential zonation mapping, that there we use the different layers we club together, and based on the rating and weighting of the different thematic layers, we are able to get the groundwater prospect mapping. So in the same way, for the geological studies, we can also make both remote sensing and GIS uses to get the area, that which area is more active or which area is lesser active. So a comparative based study can be made for the different areas. So this is the new tectonic land deformation index, or you can say new tectonic land deformations map, okay, or you can say the RIAP, which means the ratio of informed by the active tectonics, so that how much area is active and how much area is inactive. So this methodology we have developed for this area, and we got here that which area is highly active. So class 1 is highly active area, and class 2 is as compared to the class 1, it is lesser active, and 5 classes and 5th class is less active. So based on the different thematic layers like geology, the structures, then the lineaments, slopes, and various other factors we have included here to determine the area of active and area which are not comparatively active than the other areas. So such kinds of prospect mappings for the tectonics we can make. So besides this, nowadays through microwave remote sensing, we can also find the filtered phase analysis, which also shows that which area have a high deformation rate and which area have a lower deformation rate. So these are the filtered phase images, which tells us that which area has the upliftment, or you can say the subsidence. So based on these filtered phase images, of the Sondon area, we are trying to determine that certain areas along the Chandigarh anticlines, we found here the subsidence have been taken place. Now the question is why these subsidence have been taken place. So some studies have suggested that these subsidence just above the Chandigarh anticlines are due to the heavy withdrawal of groundwater. So because of heavy withdrawal of groundwater due to the Chandigarh city and the adjoining area of Mohali, the subsidence have been taken place in this area. So subsidence and any other kinds of activities which shows the changes in the deformations, we can measure through the filtered phase images from the microwave remote sensing data. So besides this, nowadays very important and microwave remote sensing analysis are the persistent interferometric scattering techniques. So this is the methodology we have developed for P-INSAR analysis. These analysis helps us to know the temporal deformations patterns, that over the period of time we use multi temporal data, and we are able to get that how much deformations in centimeters or millimeters have been taken over a decade or 2 decades. Regarding that, we require a very large amount of data. So based on that, we have find in the Rishiganga area that which area have high velocity rates. So this is the velocity map where the catastrophic floods have been taken place. You find in the Rishiganga area, these are the area where you have a high catastrophic velocity of the rocks. So such velocity means that how much rocks are displaced from the particular place. So such kinds of important and very informative, and you can say the latest kind of technology which is going to be used or people are using around the world regarding the deformations or tectonic analysis are there. So this is the time series analysis for cumulative displacements. We derived from the Sentinel data from 2017 to 2020. The variations deformation patterns is marked by the positive and a negative correlation, where the positive value showing the uplift and negative value showing the subsidence. So upliftment and subsidence is the main concern we generally measure from the P in SAR data. Whereas in the morphotectonics, we generally determines the horizontal variations. So then many other kinds of study we can make using like the seismic microzonations, the shear wave velocity, so mapping of earthquake related geological hazards. So in the Dehradun Valley, such kinds of studies we have made that based on the profiles, by using the resistivity imaging tomography instrument, we are able to make the velocity maps. Such velocity maps are also helps us to know about the deformations patterns over any area under investigations. So this is the map of the Dehradun area. This is the Dehradun area, and this is the, you can say, your Jamuna river, and in this side we have a Ganga river. So we have made certain resistivity image locations. So resistivity survey we have made here in the Singuli, and in the Bowala area we have made the resistivity surveys, and based on the resistivity surveys we are able to determine that whether this area is active and what is the reason behind the activeness, or you can say the why the area is so active below the surface of the earth. So based on the GPR and earth resistivity image tomography surveys, we are able to get, and we find here that due to a particular kinds of rock, which is mentioned here, that 5 earth resistivity imaging topography in the Kandigarh area showing the water saturation zone, that this may be the water saturation portions that we are able to get, even though this is the these resistivity image topography map is from the Mussoorie area. This we have published in the Groundwater for Sustainable Development journals, where we are able to get that how streams and springs are making way for the water accumulation. So this is the way that BES vertical electrical soundings results obtained from the NFC schools campus, showing sharp point more than 100 micrometers resistivity. So if the resistivity is very much high, this means that the water saturation zones are found there. So these water saturation zones means accumulation of more water below the surface of the earth. Besides this, interannual groundwater storage variability over the water-stressed regions of Uttar Pradesh, Haryana, Delhi, Punjab, we have made such kinds of analysis, and by which we are able to get that certain areas are quite water-stressed area in these states, and whereas some areas may have recharge is very much high, even though most of the area we find that rainfall is lesser, as rainfall recharge is less as compared to the discharge, or as compared to the water explorations from the groundwater for domestic irrigation and industrial purposes in the heavily populated states of northern India. So These are the map we have developed during the pre-monsoon and post-monsoon. So you can find that in the pre-monsoon rate, the groundwater storage capacity rate is very much high in the hilly area, very much high in the plain area as compared to the hilly area. Whereas in the post-monsoon, we find that it has been shifted up to a certain extent. Then this Kedarnath tragedy, which have been taking place in 2013, we have also made certain kinds of analysis that why the tragedy along the Mandakini and Kedarnath temples have been taking place. So such studies have been also published in the quarterly international journals. So you can see that various things that how we are able to monitor and map a very small movement along any hills or along the any surface, whether it's a plain or hilly area. So even though the landslides we are able to monitor from the satellite data. So landslide hazard simulations mapping and landslide hazard studies and landslides movements corrections we are able to measure from the remote sensing data sets. So one of the famous Kaliyasur landslides in the Garhwal Himalaya. This is also published in the Quarterly Science Advances, which lies in the Pori Garhwal area. So based on the RAMS soft modeling simulations, we are able to predict that what is the rate of velocity of this Kaliyasur landslides. So result showing that what is the output jump height, kinetic rock energy, velocity jump height, and maximum pressures and maximum height by which the landslides may take place. So these are geophysical studies for detecting the bedrocks for the installation and monitoring of this. This is in the IIT Mandi campus in Himachal Pradesh. So resistivity imaging tomography survey have been made, which the result shows the GPR and resistivity imaging conformally shows that saturation zones are marked by the GPR data as well as earth resistivity tomography at very same location. So which shows that geophysical techniques are quite helpful in detecting the water below the surface of the earth. So this is also the advantages of remote sensing, that by such techniques we are also able to get the information below the surface of the earth more accurately. So then this is also the geophysical study regarding the detection of groundwater. So these blue lines showing the water availability below the surface of the earth. So these are all for the landslide. This is for the landslide detections, that how much landslide is, if the landslide is taking. So this portion is the landslide area. So and landslides are heavily taking place. So throughout the year. So this is the pre-event and post-events. You can find the difference regarding the landslides, and this is the GY images, which showing the scrap face and landslide material which have been dumped here. So earlier this was, so this is the landslide. So you can find the difference. This is pre-disaster and this is disaster. So where we have right landslides, so this landslide having accumulated, landslide material have been accumulated here. So this is all for the study regarding the water findings below the surface of the earth. So water prospecting mapping gives us the information about the surface of the earth, whereas GPR or geophysical methods, these are also helpful directly to know about what lies beneath the surface of the earth in terms of water. So this is the landslide studies. So this is the possible subsurface slip surface. So here we have marked the changes, that if there is some kinds of faults which lies below the surface of the earth. So this scrap faces we are marked here. Then again this is the shudder. particular image is we have prepared from the Astra data. So you can find the quality of the data which showing very clearly the hills and the mountain fronts in the Doon area as well as in the Mohand area. This is the Chandigarh arc, which you can see the Pinjore Doon, earlier the Pinjore Doon area in the Son Doon as well as Pinjore Doon. So you can find here that how remote sensing data are able to provide us the information about the surface, digital topography. So then analysis can be made in such a way regarding the tectonic deformations, if any kinds of faults are there. So here the geophysical studies are showing here that fault surfaces below the surface of the earth. So satellite optical remote sensing data provides us the information based on the drainage streams. Okay, our vegetation sometimes also helps us know that what lies beneath the surface of the earth. But geophysical techniques aided with the remote sensing helps us to know at what depth, what kinds of displacement and deformations have been taken place. So these are all studies related to the geophysical techniques we have made. So then the landslide hazard generations, which can also be made. So different zoning, that which area is highly active and which area is lesser active. So such kinds of studies we can also make from the for geosciences point of view using remote sensing. So this is landslide hazard inventory map, then geomorphology and NDVI. So all these thematic layers can be clubbed together by using the weighted integrated overlay analysis. So weighted integrated overlay analysis can be used for the groundwater prospect mapping, then land surface detection mapping, landslide hazard zonation mapping, whether it's a flood hazard zonation mapping, any kinds of final output map, which is known as the GIS-based analysis. So GIS-based analysis can be made for the geosciences, water sciences, landslide hazard zonation, microseismic zonations, or any other kinds of investigations. So these are different thematic layers related. Then the suspectability map, where the landslide is very much high, active or low. So you can do the highly suspectable zones have been marked here. So these all zones have been marked by using the certain thematic layers we have derived from the dam. Then stream distance, slope, linear and soil textures. These are all we can directly generate from the dam data. Then soil, as I have told you that National Bureau of Soil Science and Land Use that is located in the Nagpur, they provide the thematic layers of soil texture map. So throughout the India, you can get all kinds of information regarding the soil textures from there. So various thematic layers like NDVI, geomorphology, land use, land cover. So all these clubbed together, we got the suspectability mapping. This is also the rock slide triggered in the Rishi Ganga and Dhauli Ganga. So 2-3 hour publications have been published regarding by using the different technologies, that why and how it happens. So earlier I have showed you that how by using the microwave remote sensing data, that how much displacement and what was the velocity at the time of event and before the event, how the rock had been triggered and what was the triggering event. So then micro seismic stations which are located in the Uttarakhand area. So these all helps us to know about what happens in the Uttarakhand, you can say the Rishi Ganga Valley, where the catastrophic floods have taken place. So, and then certain study by our partners having made for the groundwater prospects mapping by using the geophysical techniques as well as groundwater prospect thematic mapping by using the weighted integrated overlay analysis. So that paper is also published in the Groundwater for Sustainable Development. So we use the different geology, geomorphology, slope, elevations map. So then lineament map have been shown by using the Rose diagram. So then drainage density, then land use, land cover, vertical electrical sounding, that where BES is poor or high. So we are able to get such kinds of 3D scenario by using this, that where the groundwater prospect is extremely good, very good, good, poor, very poor, and extremely poor. So in the mountainous area, as shown in the three-dimensional, that here the water prospect is quite low, whereas in the plainer area, you can say that the area which have very low heights are through the adjoining area, so prospects of waters are very good. So prospects of waters are good to poor are found in the pediment zones, are zones which lies just below the hilly area, whereas the low-lying area water prospects are generally very good. So this is also the map of shivaliks in the Nepal Himalaya. So these IGS stations and various stations located in the India helps us to know about whether the Indian plate is moving towards the Asian plates and what is the rate of displacement. Our studies shows that most of the studies in the Indian Himalaya shows that Himalaya, this Indian plate, this portion is converging with the Himalayan, or you can say the Asian plates, at the rate of 2.5 centimeter per year. So such kinds of displacement, in some portions the displacement is 3.5, some portions of Himalayas it is around 1.5. But in the Uttarakhand Himalaya it is 2.4. Earlier we have recorded by using the different stations data in the Uttarakhand. Whereas in the Kashmir Himalaya it is around 2.2 centimeter per year. So maximum, these are the different stations located. And this is the rate of the placement map. This is very typical crustal deformations. So this is also the seismic activity over the period of times. We have marked this. This is for the Dehradun area. This is the Nepal Himalaya, and this portion is the Chandigarh and you can say the Pinjovardhan area. This is the Kalam belt. So various stations, various GPS stations have been located in the Uttarakhand portion of Himalaya, whereas in the Uttar Pradesh we don't have any major stations except a few stations. But in the around the Dehradun and Mussoorie and above that, various stations are found in the Sasnagar, Rupnagar, then Dehradun, Rajpura, Mandi are some of the typical stations by which provides the crustal deformation and strain accumulation study data, the time series data. So such kinds of crustal deformation studies, which helps that how much rocks are converging, what is the rate of converging, we are able to detect. Earlier in these presentations, I have shown you that what was the basics, that morphotectonic analysis helps us to know about the horizontal displacement of the rock, and by using the different indices, then geophysical methods, that if we validate remote sensing, morphotectonic, which we determines from the remote sensing data with the geophysical techniques, and after that I am showing you that how the crustal deformations about the larger area in the subcontinent extent, that how these things are moving by using the GPS data, or you can say the various stations which are located, which are also known as global navigation satellites data. In other words, this is very emerging technology nowadays, that all kinds of seismic studies are now based on the this GNSS stations. So this geodetic deformation with respect to hydrological loadings, we can also validate it with the gravity data by which we'll get from the GRACE. So you can find here the seismic periods by which the deformations have been taken place. So these are the various studies we have made from time to time in the Nepal as well as in the Himachal and Uttarakhand Himalayas. Even though some studies we are now following in the Jammu and Kashmir Himalaya regarding the GPS cluster deformations and the SAR-based microwave analysis. This is the INSAR cluster deformations, which are also showing the rate of deformations. So this is the deformations map which we are observed using the LOS-1 satellites for a certain period of time from 2007. So this is all about the today's presentation.
Thank you, sir. Any questions, please? There, Sunil, there were, and others. The session is open for discussion.
Yes, sir. I have the question from first presentation.
Okay, just I'll open the
Ajay,
GG.
you have explained the digital number thing in one of the slides.
Okay.
Yeah, so I have a question related to that. The digital number correction is an automated process where we give required input as you told that it will be available on the image, or it's a manual performed process, manually
It's a
performed process.
manually, generally we manually do it.
So there is no automated thing to identify and rectify it. Some kind of tool or something.
Yeah, it can be digital number can be enhanced, but generally I have not applied any automatic corrections for regarding the digital number, but generally we made it manually. But I think there may be some methods in the RADARS Imagine where we are automatically it can be performed to enhance the digital number. Certain kinds of things can be performed automatically also, but it is not so accurate. But if we accurately correct the digital number, that can be manually. We can perform that manually.
And sir, normally, how much like the percentage of error occurs? So it should not be a very hectic process to perform manually.
20%, I think, up to you can get the better image which can be used for your analysis, but it cannot 100% you can get the corrected image by using all these kinds of corrections. But for a certain extent, up to a certain level, the image can be corrected by using if you using all these kinds of corrections by using the various filters. Even though the many filters are found for various kinds of analysis like radiometry as well as atmospheric filters are there. But these filters are not very common in the this open source software, whereas in the proprietary softwares, I think in the high end softwares, very good quality filters which can reduce the errors up to 90%. Whereas in the open source software, which is Saga as well as Quantum GOS, up to 16% corrections can be made.
Okay, sir. Okay, sir. Thank you.
Next.
Good afternoon, sir.
Very good afternoon.
Sir, I have a question, sir. Should image classification be performed before radiometric correction or after radiometric correction?
It's up to you whether you wish to correct your classified image, but generally we prefer it before the classification of the image.
Okay, sir. Thank you, sir.
Any other?
So, any participant who wish to ask me about the geosciences? Are you able to get anything from the geosciences PPT?
Yeah. I'll be now, some of the questions are there, they have written me personally, so I'll be asking it one by
Okay.
one. So I'll be asking you 3 to 4 questions because there are a lot of number of questions. I cannot take
Hmm.
each and every question. So I'll be taking few major. So the first question is ki how this remote sensing and GIS imagery can be used for identification of different kinds of rock types.
So first, I think first you should have a better knowledge of rocks. Then only you can use the remote sensing satellite data for identification of rocks. If you know about the rocks, that what are the conditions or what are the qualities of the rock by which the rocks are formed. So if you know about the lithology as well as the rock contents, then only you can identify by using the remote sensing. By directly, you can't identify that which is the what kind of rocks if you don't have any knowledge of geology. So only geological people who have a sufficient knowledge of geology that if such and such rocks, but maybe the water content or other kinds of properties of the rocks, only then we are able to identify through the remote sensing. Directly, a layman or a simple person who knows about the remote sensing, they are not able to get the information about the rocks. They can generally differentiate that this one is different, or you can say the differentiations can be made, but to know about that what exactly the kind of rock or type of rock, it's very difficult without knowing about the geology of any particular area. Or in time it determines that this may be the igneous, sedimentary or metamorphic rock based on the image interpretation, but we can't exactly determine that whether it's a granite or it's metamorphic rocks. In general, the tendency is that even alluviums, which is alluvial materials, then younger alluvium, old alluvium, such kinds of things can be determined very easily because any material which is adjoining to the river, that can be a part of the river alluvium. So you can say that it's a younger alluvium, and the adjoining to the younger alluvium may be the older alluvium. So that things can be determined rather the other portions of the rock.
Second question is ki, from where do we can get the GRACE data and what are the softwares through which we'll be handling it?
See, GRACE data, we can get the GRACE data freely downloadable from the GPL NASA. There is a one website which is known as Giovanni. From the Giovanni, you can, if you anyone wish, you can get a link from me, so they can get the link for the GRACE data. Then GRACE data needs certain kinds of processing because it's a data in bulk. So we have to club them, and if you know the better programming, so you can make the GRACE analysis very easily. Otherwise, if you make the every tile-wise analysis, then it will take sufficient time for you. But GRACE data is easily available in the USGS Explorer and the NASA GPL Giovanni satellite portal. From that, you can get GRACE data. So it can be processed even though in the ArcGIS. In the ArcGIS software, you can do all kinds of analysis by using for the GRACE data.
Sir, another question is that which data will be better for interpretation of geomorphological features, indicators, whether optical data or radar set data?
I think optical data is better for the beginner, even though for the high in the research, they are also using the optical data. But the problem of optical data is not available for the, or you can say the quality of optical data is not good during the monsoon. However, for the geological purpose, you can use the any seasonal of data. So I think optical data is very much useful for remote sensing in the geosciences.
Especially for geomorphological features?
Yes, that is optical data is very much important, and Landsat data. If you have a list 4 data, that is also very good data. But Landsat 30, Landsat 8 data is beautifully can be used for extracting all kinds of, even though minute information, even though nowadays people using the ArcGIS by using the Google satellite imagery, okay, they can be used for any kinds of analysis, even though by finding the small potholes and braided bars and channel bars from the satellite data. So optical data is sufficient for any kinds of analysis for the remote sensing. Except nowadays the advanced techniques like beams are they required, or microwave remote sensing, which can provide the better capability for more accurate information. But for the beginner, optical data is very good.
Another question is is there any indices available through which we can highlight the structures? Structures? Any specific indices for highlighting structures?
No, we can. The morphotectonics are these are the relative displacement techniques, that which area is more active or which area is less active. Although from to find about the faults and folds or any kinds of structures, the drainage. If you able to better, if you are able to better interpret the image, you can directly get the information from the satellite imagery that where the fault is going from the satellite data, and drainage patterns are quite helpful in this way. So image interpretation is very much important. If you are able to interpret the image, then you can get all kinds of faults and major structural events and structural things which are found on the earth that can easily be marked using the optical data. So there is no such indices which mark the structures. Structures can be marked only through the satellite images. Indices is for to know about the deformations, which area is active. These are the quantitative and qualitative interpretations. For the qualitative and quantitative interpretations, we do the this morphometric and morphotectonic analysis.
Okay, thank you. And the last question I'll be taking up that says, is there any filters used for highlighting structures? Any specific filters in the mountainous terrain for highlighting structures?
I think Laplace and Gaussian filters are quite useful. I don't know. I have even though I think Laplace and Gaussian filters are quite useful for linear detections, and high pass filters can be useful for the structures, major structures. But I know if you have a good quality of optical image or better optical image, you can directly get the major structures which lies on the Earth surface. You can get from the satellite image directly and mark it in the GIS also.
So I feel that it's over. I'll not be taking up. Otherwise, it will. Still, if I have not asked any of the questions from I've left out, you're free to ask anyone. If not, then we are going to end the session.
Sir, which data set are useful for identifying geological or glacier surfaces of
So
glacier landforms like moraines, etc.?
glacial and moraines landforms, if you mark them very accurately, and if you know about the ArcGIS, in ArcGIS, today we are able to get the Google image. So from the Google image, you can mark all kinds of glacial geomorphological features, even though the debris covers where the snout of the glacier, where are the horns, and all these major glacial geomorphological features can be marked. And if you have a better GUI data or copper set data, then also you can get the information. But freely available data is Google data, and GIS is quite helpful. I don't know whether the Saga GIS is have the option to get the Google image inbuilt, whereas the ArcGIS have this option that you can browse the Google imagery in the ArcGIS and make all kinds of analysis.
Sir, can we predict their movement like we does in land use land cover?
Yes, that kind of movement we performed using the microwave remote sensing data, that glacier velocity analysis in microwave data we can do, even though in the optical data there are certain methods which can be applied for knowing about the velocity of the glaciers.
Okay, sir. Thank you so much.
I presume that all the questions are now answered. And now, on behalf of Center for Climate Change and Water Research, I sincerely thank to Dr. Ajay Kumar Talur for his valuable insights in detailed study. I was so amazed that he has published such a large number of research in different aspects of application of remote sensing from glaciers to water, microwave data. So he has shown us some of the unique studies that he has done, not only using the uh, primary data of optical and remote sensing data, microwave data, but also he has used the application of GPS, GNSS series in highlighting the tectonic movement. That was the most new thing that I came to know today, that how practically we are doing it, because I had some confusion in that. Now, after listening today's presentation, my doubts were clear. So I thanks a lot again that you have enriched us with the ocean of knowledge that you have, and in future also we'll be expecting the same blessings from you to my center and my uh, students, and in future some of my students will and the research scholar will try to take some valuable guidance so that they can also come up with good and sound publication. And with this, I again thank you that you've given us the time to my students. Thanks.
Thank you, Surajit. I also thankful to all the persons who are associated with you for successfully conducting this course. Even though I also wish that any participant who wish to work and learn the geosciences, they can contact Suraji, and even though contact us if they wish to bring some quality publications in the JS, and who wish to research in the geosciences as well as in the water sciences for a larger domain. So thank you very much for all.
Thank you, Ajay for such an enlarged view of geological applications and role of remote sensing in the same. And we wish you good luck, as well as we'll seek for your guidance to our students in future
Okay,
also.
thank you.
Thank you.
Namaste. Thank you. And with this, we end our day 10, session 1. We have completed. Now, in the second half, again, we'll be meeting by 2:05. We'll be starting up. So please do join us by 2:05. How was the feedback for today? Anyone? How was the day? Excited?
Yes, sir. It was very good,
None?
sir.
Yes, sir. Acha.
Yeah. Because they are,
Yes, sir.
they are the.
Sir,
हाँ बोलो
first
बोलो.
section was everybody.
आवाज नहीं आ रही तुम्हारी.
Sir, first session I feel for myself was very interesting. Specifically, the flight errors which sir explained, that was very mind blowing for me. That I was not expecting these many kind of errors due to every movement of the flight can occur while capturing the images, which I came to know in the first session, sir. Thank you.
Yeah. Second speaker was too good. He has shown a lot of application. You see the publication what he showed, and the kind of diversification, the quality of map, the quality of publication. That is not a smaller thing to do it. Getting one paper published in one journal with 5 impact factor, it will take 5 years to as a student if you are not working well, and even if maybe in entire life you cannot have such a high publication, so impact factor. And if he is constantly publishing, it means that the quality of research, what database and the kind of models he is framing up the kind of things that he has presented was very मतलब मेरे को तो बहुत ही अच्छा लगा. मतलब इतना सारा काम किया हुआ, मतलब बहुत मेहनत लगता है. मतलब एक मैप जो वो स्पेशली जब हिमाचल मतलब हिमालयन टेरेन का जब आप मैप बनाते हो, इतना कॉम्प्लिकेटेड है और इतना मुश्किल से डेटा मिलता है उसको करना. वो हो मतलब अगर आपके पास अच्छी टीम नहीं है, अच्छी सोच नहीं है, पब्लिकेशन करना बड़ा मुश्किल है भाई. डेटा एक्वायर करना, फील्ड में जाना बहुत टफ है. लेकिन चलो हम लोग लकी हैं कि इतने सारे लोग बाग अपना जो बेस्ट ऑफ नॉलेज है वो हमसे शेयर कर रहे हैं. एंड वी आर गिविंग यू ऑल द नॉलेज एट अ सिंगल प्लेटफॉर्म. नो, वी हैव all free. So and the credit goes to Dr. Shruti again. I say that she has arranged the program in such a way that every day we are having some new speaker, new faces with new topic, and always you're learning. Maybe somebody who is more keen towards geosciences, like my students from BSc Geology, they can interact with him. Also, the persons who are from civil engineering background can look always whenever their unshul is there. So they can have a continuous monitoring and guidance can be taken, and they can also come with good sound publication, because at last of the research whatever DST has funded us will be proved if we are coming up with a good publication. So that was the target they have given us, DST has given us, that at least we should have at least one or two Web of Science publication. But I doubt the kind of, because many of the persons are not well in your group also. And let's see whether we can come up with those kind of research publications. That's a matter of time. That time will decide. But right now, I don't have any hope with the kind of progress that the participants are showing till date. Further, I don't know. ठीक है, तो फिर हम 2:05 में फिर मिलेंगे. तब तक के लिए नमस्कारम. ठीक है, बाय.